Prova. Welcome everyone. I would like to introduce our keynote speaker of this morning. He's basically the fan #1 of PyCon Italia. I think he attended from PyCon 1 to this edition, and I think he spoke at every edition, maybe except one, yeah, but because he's lazy, you know, yeah. So he started spreading the word of performance in Python, starting claiming his knowledge about how to make Python faster, and started the contribution of PyPy. And today, again, he's talking about why Python is slow. Unbelievable. Yeah, unbelievable, guys. So I would like to introduce here my friend Antonio Cuni.
Hello, everyone. Thank you. And actually, yes, I wanted to start the presentation with like a kind of a personal note because like this is me in like 17 years ago. Nobody can recognize me, not even my mom. I really asked her, yeah, who is he? And this was PyCon 1, like first edition of PyCon Italy, 2007 in Florence. Like Python was kind of very strange language in Italy. Like I think we were like 98 people or something like that. And this was actually my first public talk. And so, like this conference is kind of home for me, and it's very important. So being on this stage now, it's like, yeah, I'm nervous, excited at the same time. And, but speaking of all the time that passed since that day, I mean, a lot of stuff happened, but I mean, I became friend with a lot of people at a conference. A lot of, I mean, this is actually from the last 2 years because I didn't find the old ones. And a lot of them are in the organizers. And I think that we should all say thank you to them. Yes. Because they do an incredible job for all these years. And well, I think that they never get enough credit, so yes, I wanted to do this. And like career advice for beginners, how do you get here? Well, you go to PyCon, you make a lot of friends, you drink barrels of beer, and then you hope that they invite you to here, yeah. And to be like precise, when I say barrels of beer, I literally mean barrels of beer. That this was like we were in Berlin 2 years ago. We were celebrating my new job at Anaconda, and yeah, that's a very nice moment that we all remember. And speaking of Anaconda, let's go back here. This presentation is hosted on pyscript.com, which is one project which I've been working on in the last 2 years. Now I switched. And super incredible, cool project to host browser-based Python apps, which runs in the browser. Very easy for like beginners, but worked very well also for presentation. So I think that time to start with the real presentation. The motivation for giving this talk is that I've been working on this topic for a lot of years. A lot of my career has been on PyPy. PyPy, the JIT compiler, not PyPI, the package index. PyPy is an alternative implementation of Python, which is famous for the JIT compiler, so it's something to make Python fast. And during my work on this project and related projects, I kind of got some understanding of some reason why Python is slow. But also, talking to people, I realized that some things that for me are obvious because I work on them like on a daily basis, they are not obvious at all for many people, and there are a lot of misconception and kind of not good understanding of why some performance characteristics of Python are like that. So I thought it was a good idea to share my knowledge and hopefully find something interesting here. And raise the hand. Who of you use Python? Okay, don't even, yeah, all of you, yes. But who thinks that Python is slow? Okay, who thinks that Python is fast enough? Okay, so why are we here? So the first myth that I often encounter by talking is exactly this one. Python is not slow, and it's fast enough. And it's kind of true for certain use cases. The sub-myth is that a lot of people say, well, Python is just a glue language, or nowadays the cool thing is, well, only the GPU matters. Like we want to do AI run on the GPU. So if Python is slow, we don't care. Because all the important stuff run in the compiled code inside extension or GPU and etc. And if Python is slow, we don't care. This is true, again, for a certain set of programs. This is the set of programs that all the people that raised their hands before, thinking that Python is fast enough, but they are in this category. But in my experience as a freelance and consultant to help companies to make Python fast, well, there are a lot of programs which falls outside this category, and we'll see why, basically. So for this person, it's important to make Python fast or faster. But actually, we started 17 years ago with 98 people in the World Conference. Now we are 800. And we want to grow. And the amount of all possible programs is much larger than one that Python can be used nowadays. And it would be nice I love the language. It would be nice to be able to use it for more than just what we can. So I think that performance is an important aspect of this. And so yes, Python is not slow for the kind of program for which it's not slow, yes. But in general, we can do better. And the broader topic of this is that, yes, even if for your particular use case, Python is not fast enough, well, you can just rewrite the part of programs which are slow in C or C++, so you make fast only the parts which matter. And this was actually true until a few years ago, but now, well, it seems that everybody uses Rust and not C++. But the same argument apply, actually. And what is the idea? And again, it's not false, but it's a bit misleading, I think. The core idea is that there is this principle, we call it Pareto principle. At this point, I was tired already of writing slides, so I asked ChatGPT. I'm here writing a talk about performance, and let's explain the 80-20 rule. And what is the 80-20 rule? I don't feel like reading ChatGPT. But basically, the idea is that very often you have 20% of the program being accountable for 80% of the actual time spent running. Or it could be 90-10, but it's a small part of the program is where you spend most of the time. So you can just optimize that small part and you get a lot of performance, which is true. Although then you quickly encounter this other principle, Hamdall's law, and which basically says that when you are a system composed of two parts, if you optimize one a lot, well, then the other one becomes prevalent. And then it imposes like a kind of theoretical limit of how much you can get by making this part faster. And I think it's very easy to visualize it. So we start from a Python program. Let's use the mouse here. In which you have the inner function, which takes a lot of time, like 80% of the time in this visualization, and the rest of the program, like 20%. Then you rewrite it in Rust. And in this, like, we make it 10 times faster. And believe me, it's not easy to make it 10 times faster. And, but then, like, the rest of the program is the bottleneck. It's no longer the Rust. And even if we make this function 10 times faster, the overall gain is like 3 times, something like this. And which is, okay, it's good. Yeah, we made your code 3 times faster, but if you need like a real 10 times speed up, well, you cannot with this strategy, basically. It's like theoretically impossible. And yeah, could be good for some use cases, but I mean, you see why you quickly enter into problems. And it's something that I actually saw in my career. Like, it's kind of easy, if you know how to optimize what's called the inner loop, which is the bottleneck, but sometimes, at some point, you no longer have obvious bottlenecks, and you don't know where to go with this strategy. And then we need to try to optimize the rest of the program. And then, well, a lot of people have this idea, like Python is slow because it's interpreted. So what does it mean exactly? Like, when you run a Python program, well, you run it using the Python interpreter, and actually what it does is to take your Python program, translates it into Python bytecode, and runs in the Python virtual machine. And this is what we call the interpreter. And it means that every single operation in line, like if the A equals A plus B, well, every single operation is interpreted, but it's run by the interpreter, and then you get the result. So interpreters are famous for being slow, because instead of translating to machine code directly your program, and so that machine code can like avoid this process of reevaluate the same code again and again, you have to redo the work at every line. A very, very short explanation. And so you could just write a compiler instead of an interpreter. That's kind of the idea. And again, the sub myth of this one is, well, some big company in USA just announced yet another project which will use LLVM, so it will be fast, and then all the problem will be solved. I've seen this a lot of times, and most of the time they don't work. Why? Because the interpreter is only a very small part of the problem of Python. Imagine to take this very simple expression, like pi.x times 2. If you're writing in a low-level language, C, C++, Rust, you can compile this code to, well, do something very simple. You locate the address in memory of this expression, p.x. You load this in memory, you load the 2 in memory, you multiply, and you store the result in the target variable. But if you do it in Python, no matter if you are interpreter or compiler, there is a lot of logic that you need to implement if you want to comply with the semantics of the language. And a lot of logic is like this. I don't know how many of you are familiar with like the internals of Python, but it's like we need to look up p. To start with, where is p? Well, maybe it's a local variable, maybe it's a global variable. Well, we do it dynamically at every time. And an interpreter, a compiler, cannot help much. But then, yes, what is p.x? Well, C compiler can just know where in memory it is. But for Python, you need to find a type, call $getAttribute on the type, which could be a user-defined function, so you call other Python code, and then, well, time passes. And then you have pi.x, and then you want to multiply by 2. But then what does it mean? Depends on the type of x. So we get the type, we call this dunder mul on the type. Wait, Maybe we need to call rmul. Who knows the rule when you call dunder mul and when you call dunder rmul? Nobody? Okay, someone does. But I mean, all this stuff, and then we go, well, we continue, blah, blah, blah. All this stuff must be taken into account by any compiler. Like, if you want to implement Python language and not some kind of random subset which looks like Python but is not Python, you need to take this into account. And this is where you spend most of the time anyway. So if you just take a compiler and take Python and compile it to machine code, then the machine code does do all this stuff, well, it will be slow. And that's actually what happened multiple times. So yeah, this is not really the solution. So kind of the problem that I'm trying to say here is that when you want to do this operation, well, we don't know the types. So what can we do to improve? Well, nowadays, we have static types in Python. You can type functions and notate with types, so a compiler can have a much better and an easier job at producing good code. So in this kind of slides, I want you to think like a compiler. So imagine that you are a compiler, and you have this Python code, and you need to imagine which machine code to produce to be fast. But you don't know how this code will be used. I mean, there are various techniques for implementing compilers, but let's stick to the simple one. Like, you have a function, and you need to produce the code for this function. So I have this very simple function, takes two integers, returns an integer, x plus y. So we can do like C and Rust. Well, just load the values in memory, add it, return. And, well, this works. Print, just works. So we can. But the problem is that, like, if instead of adding 2 and 3, I add hello and world, this is a perfectly valid Python program. It will work, because type annotation are actually ignored by the interpreter. And yes, we can use them as documentation. We can use tools like MyPy or PyWrite to get some kind of understanding and be more sure that our types are correct, whatever it means. But the interpreter or the compiler, well, cannot take for granted that the types that I declare are correct. It must take into account all the possible possibilities. Else it's not Python again. And you could say, yeah, sure. You are kind of cheating, because here, imagine that we are using MyPy, so I run a static type checker on my code, and I could just say that it's mandatory. It's no longer optional, and I can compile code which must comply with the static type checker, and then the compiler has an easier job. So I could just say that, like, this line, all the lines which are type ignore or similar, like no type check decorate or whatever, are forbidden and illegal. Then the compiler has a much easier job, right? Who thinks that I'm right? At this point, it should be obvious that there is something more. Like, this is still a perfectly valid Python code. I create a custom class with a dunder add method, and I have a function which takes to my class, objects, return one, perfectly works. And then somewhere later in the program, randomly, I delete the dunder add method on the class. And yes, someone is doing like this very Italian thing. But yeah, well, we can debate whether it's good idea or bad, whether it's good code or not. But this is Python. This is the rule of Python. Complain with Guido, not me. If you are a compiler and you want to comply, you need to take this code into account. And it's not really theoretical. I mean, I don't know for this specific case, but when we developed PyPy, we had to implement the full Python semantics, because we wanted to use real Python code. We want to be able to import Django, import NumPy, all these big libraries, SQL Alchemy. And somewhere deep in these big code bases, there are crazy stuff. And in order to run them on an interpreter which is not CPython, you need to be compatible with them. So if you want to run existing Python code, well, you need to take this kind of stuff into consideration. So static types, no. And so, okay. What I'm saying is that if you just want to take your Python program and do some kind of static analysis, like normal and classic compiler do, then you cannot do much, because Python is too dynamic, too many corner cases. So what the other classic approach, like textbook approach, well, you can use a JIT compiler. And this actually works. Apart, it's the all. The all in all your problems in this sentence is the problematic part. JIT compilers actually work. PyPy is a JIT compiler and managed to make Python code very fast in certain cases. The CPython core development team is developing a new JIT compiler for CPython, which shares actually a lot of ideas in common with what PyPy explored. And the upcoming CPython JIT compiler will make some Python code fast. So it's actually a good thing. But then we quickly go into other problems, and these are very subtle, but I think that especially now that CPython is getting a JIT, they will become kind of prevalent in the Python world. One problem is that we have this kind of trade-off triangle. And you can have dynamicity of the language, you can have speed, and you can have a simple implementation. Well, pick two. You cannot have all of them. Like, in the last 30 years, CPython was on the left side. You had dynamicity, because the language is very dynamic, and you had a simple implementation. Simple with an asterisk, like CPython is a complex piece of code, but the implementation of the interpreter and the logic was kind of, well, textbook. You take your AST, you compile to bytecode, you have a virtual machine which interprets the bytecode. Everything was kind of easy to read. Like the C code of the CPython interpreter is very well written, very documented. Like if you are a student at the university studying this kind of topics, you can probably understand maybe not all of it, but some of it, and then if you spend more time, it's something doable. But if you want speed, then yes, you need a JIT compiler. For those who don't know, like a JIT compiler is a just-in-time compiler. It means that basically you run your program as with the interpreter, and then while you run the program, the interpreter collects information about what's happening. So for example, these two variables in this particular piece of code, they seem to be often integer or string, so I generate fast code for these cases. And then if something changes, like if some crazy guy deletes down the road on the class, then I can invalidate the code and generate it again. It's an incredibly complex piece of code, but it produces good results. So yeah, you can have a very complex implementation, keep your dynamicity, and get good speed. But then you quickly end up into what is the real problem of this approach, from my point of view, is that you lose predictable performance. With CPython, simple, like until 3.13 at least, it's very easy to predict the performance of a piece of code. Like, if you look at the bytecode produced, well, you kind of know that loadout takes, I don't know how many microseconds, and the store out some other. And I've seen colleagues in some companies doing exactly this kind of analysis, trying to optimize code by removing the bytecodes and knowing how much each bytecode costs. And this is very useful because you can see a diff of a pull request and kind of predicting or having kind of intuitive understanding of how the performance will look like. But if the implementation is no longer simple and starts to become complex, then you don't know, because the compiler does crazy stuff. And in order to understand how the performance looks like, you need to know very well what the JIT compiler does. And know that in this particular case, if these conditions are true, the optimizer can remove all the overhead and produce fast code. And if other conditions are not true, or this code is slightly different, then you don't know. And this is actually very good career advice. Because if you are one of the few people who understand how the optimizer works, well, you get paid for doing this kind of stuff. That's what I did for 10 years. But like in general, it's not super useful. I mean, it's useful. Like PyPy, as being useful, is still useful. You can use it for having fast code. But if you want to use it for super good performance, then it becomes hard. And then you arrive at the problem which I call optimization chasing. And it's, I kind of predict, maybe I kind of fear that, well, CPython will go into down that route. Like, you start with a slow language, well, Python. And then you add optimization for what's called the fast path. Like, basically, the idea is, again, I have code, and I need to take into consideration all possible crazy stuff, but in practice, the crazy stuff doesn't happen. So I optimize for the fast path. And then I have something which is either same speed as before, because the optimization don't kick in, or it's faster. So everybody's happy, job done. Okay, I don't know what I wanted to say, but okay, sorry. What I wanted to say was good job, but yeah, whatever. But then what's happening is that time passes, and you start to rely on this kind of optimization, because you are writing code, and I write a library, I want it to be fast, I use all the kind of tricks which I know the optimizer will use for optimizing Python code, or simply, I have a program which works, and it can do this number of requests per second, or takes this number of seconds to complete, or whatever. And then time passes, and I'm sure that my code is still fast. Because what happens often is that I do an unrelated change somewhere, and then I get to time slowdown. And it's very, very hard to track it down. And again, well, I did it for a living for a while, but like it's like it quickly becomes impossible to do reliably. Like, you can optimize at a specific point in time, but you need to be an expert for it. And then you leave and you do something else, and then other people change the code, and then who knows what happens. I remember this time in which the code was suddenly very slow, and we didn't understand why. And then it was because it was still Python 2 times. We had a dictionary which contained only strings, and then at some point we put a Unicode string at the key in the dictionary, and then this was enough to kill one optimization, because you were no longer sure that all the keys were strings, and then you needed to do a lot of checks, and everything was very slow. But I mean, this kind of stuff happened, and how do you track it down? Well, you need to look at the assembly code, not easy. So, what is the actual problem that I'm trying to hint at? Like, we have all these possible solutions, and from my point of view, none of them work very well. What is the actual problem? Why Python is so hard to optimize? And I think that you can have a kind of understanding by looking at this code. I call it humans versus compiler. So if you look at this code, like you are reading the source code of some real world project, you know what is happening. Like, I'm importing NumPy, yes, sure, it's very obvious. I'm doing this calculation, I get arrays of floats, I get k, which is a float, I call this stuff, I call it .sum function, which is implemented in NumPy, I add the 10, well, it's a constant, it's obvious. But from the compiler point of view, none of this it's possible to know because of what I showed before. A lot of things could change. For all I know, NumPy could be non-NumPy, because in Python you can hack the import system, and I could say that import NumPy, maybe it's something else, or not the NumPy that you think of. So, but this code never happened. In practice, this code is true. Like, it's using NumPy and for doing the sum of an array and multiply. It will never pass a code review if you do something completely crazy. So from my point of view, we have too much dynamicity. Like, dynamicity is what makes Python slow. So we could also just remove it. Why do we have all this crazy stuff? I claim that it's also what makes Python awesome, because you can just use Java if you don't want dynamicity. But who likes to use Java? Okay, any Java? Yeah, okay, yeah. Sorry, sorry for the Java shaming. It's just an example. Like, it's totally. I mean, Java is a totally fine language for some use cases. I hope that to see some people saying this again. But like, the feeling of the language is very different. Python is dynamic, and the dynamicity of Python makes it possible to write awesome libraries. You can have SQL alchemy. which you write just your model as a class declaration, and you get all this cool stuff with databases. You can write fast API, which generates a lot of code automatically for you. You can have NumPy. All this stuff are not possible in Java, so the dynamicity of Python actually is what makes it possible to write all the nice libraries that we like to use. So we need to, yes, find a balance. Speaking of dynamicity, this is a collection of, well, crazy stuff that can happen. You have very simple class point, two attributes x and y. I have a foo function which takes a point. I don't believe the type annotation because who knows type annotation? So I assert that's the instance, and then I print the .name. So does it work or not? Maybe, because it's totally possible in Python to do something like this. You create a point and you add an attribute to the instance outside the init, and this actually works. Again, well, we need to take this into consideration when we implement the language. Is it a feature that we need? Maybe, maybe not. We can discuss. But you can do crazy stuff. This is a class that has a method 50% of the time, depending on randomness. So if I run this program, maybe it works, maybe it doesn't, I don't know. And believe me, this works. Like, it works in the sense that it does what I'm describing. Like, it's totally fine Python code, because inside a class statement, well, you can have statements, like you can have ifs, you can have functions, you can have for loops. Do we need it? Don't know. More crazy stuff. Other simple, very simple class. I have a student, it takes a name, and it has a method for studying. Yeah. But then I have a Berliner. Who lives in Berlin here? Few people. And then, well, Berlin people go partying. And note that the class Berliner is not even a subclass of student. It's completely unrelated. And then I create a person, and I call a function, go to Berlin, and then I call study. What's happening here? What do you think it can happen? Well, I can do this. I can change the class of an object after the object has been created. And know that, I mean, the .name is still there, but just the class is different. So when I call .study, then I call Berliner.study instead of student.study. And yeah, this is something that you need to take into consideration again. Makes Python slow. Another example. I have a class person, I have a class student, and here I'm instantiating a person. It takes a name and an age, and I print it, it works. And now I am sure that this is a person, come on. Like, I'm not calling anything else in between. What kind of trick can I do? I can do this. So in Python, you have the dunder init, which is what everybody uses, but you also have dunder new. And dunder new, you can do crazy stuff, including returning an object which is completely unrelated. Like in this case, I'm using it for saying that if the person is minus than 19, then I assume it's a student, and I just create another class instead of creating person, and then I assign a name. But I can really do unrelated stuff. I can return 42, and then it works. Like in the sense P is 32. And yeah. Other crazy example. I have two functions, foo and bar, both return n. N is 10. I check that are the same return value. I mean, an easy way to make this failing is to well, just like change the definition of foo. But yeah, you can do it. But what if I tell you that the foo has the exact same body? Like it still does return n, but this assertion is false. What's happening here? Well, it turns out that in Python you can take a function, take the code inside the function, and tell the interpreter to use a different dictionary for globals. What's happening in Python is when you do n, here return n in the expression, and it does a global lookup. So it checks what is the dictionary of the module, which is the globals of the function, and normally it's, well, the module, the namespace where the function was defined. But you can just tell Python to use a different one. So in this case, after I do this crazy stuff here, then bar returns 10 because it uses tscope, but foo returns 20 because I just telling it to use another scope. And again, you can say, yeah, sure, but who? Like, no, nobody does it. Come on. Like, this is, yes, it's cool, it's nice, tricks. Turns out that this is real code on GitHub. And this is code from PDB++, which is a debugger for Python. And they do actually this kind of crazy stuff. So does anybody use or know PDB++? Not many people. You should. Like, trust me, it's awesome, much better than the default PDB. Pip install PDB pp, and you will not regret it. It's basically hijack the import PDB mechanism, so you don't even have to change your imports, and you get color, syntax lighting, tab completion. And by the way, like, this is who wrote the code many years ago. And I claim that it was actually very good. I mean, I can explain it later if you want, but I think it was. It actually made the code better by using this trick. But then it makes my other life as a compiler expert, a Python implementer, much harder. So yeah, I need to balance myself. But from some point of view, all this dynamic stuff are useful because they let us to have to build abstractions. And actually, it's what you do as a programmer. Like, at the end, you have machine code, 0 and 1, and very low-level operation. And then with low-level languages, high-level languages, libraries, we build abstractions over abstractions to make complexity manageable. And it's good. It's good to have abstraction because it makes it possible to write more complex programs. But in Python, every layer of abstraction has overhead. I call this, I mean, there is a kind of abstraction which is like Python to Python overhead, in the sense that I start, for example, for a simple Python code. In this case, simple algorithm, I take a list of points, which is every point is a tuple of numbers, and then I do some computation, random function. I sum all of them, and I return res. Okay, there is a typo, but okay, it's not important. And but then, well, I want to put it into a function. So I put this code into a function. Turns out this is slower, because in Python, every time you call a function, well, you need to pay the penalty, speed penalty for, well, calling the function, passing the arguments, and etc. And then maybe I want to represent points as a class. This is like much nicer code from some point of view. But again, the fact that it's in a class and on a tuple, I need to pay penalty every time I do pay.x and pay.y. So this code is much nicer to write and to read than the first one, but every layer of abstraction in Python imposes a penalty. What a JIT compiler tries to do is to remove some of this overhead, but it cannot remove it completely. And it's kind of overhead that, for example, in C, you don't have. So, well, we are back. Well, let's rewrite things in C. But even in this case, an implementation, a JIT compiler, an interpreter, whatever, has a hard time to optimize stuff, because here you have your program, which is in two languages, part in Python, part in C. And every time you cross the border, well, you need to kind of invent a protocol for making the two languages to communicate. So if, for example, I am a JIT compiler, I recognize that it's a for loop of points, and I represent all my points nicely in memory. But then I call this function, which is in C. And the function expects, well, Python objects. So I have all my nicely optimized numbers in memory, and I need to create Python objects to pass them to the function, so the function can destroy the Python object to take the real numbers. It's this kind of overhead, like cross-language overhead, that is kind of, impossible to eliminate fully. So yeah. The other problem, and this is a problem that nobody, really, literally nobody speaks about. Whenever I speak about Python performance, nobody speaks about this problem in Python. And I think it's very important, and I don't see a solution, is memory management. And in particular, we have a problem of, well, memory hierarchy. I don't know how many of you are familiar with like low-level details of CPU architectures, but in modern hardware, you have the RAM, you have the CPU, the RAM. The RAM is kind of slow, and you have level of cache to make these lookups faster. And some of your data is stored into cache L1, L2, L3. Every layer of cache is L1 is very small but very fast. L2 is a bit bigger and a bit slower. L3 is much bigger but a bit slow. And then you have RAM, which is gigabytes, but from this point of view, very slow. And then the CPU can predict which values you want next, and they try to put them in the cache. But every time this mechanism doesn't work, you have what's called a cache miss. You need to go back to memory, take the data, and it's very slow. And this is kind of animation which show you the relative speed of levels of cache. And like you see, if your data is in L1, well, it's super fast. It's kind of 2 CPU cycles. So like it's as fast as the CPU. But as long as you have cache misses and you go to RAM, well, you wait multiple hundreds of cycles. And basically, the CPU has to wait. Your CPU is not doing anything. Okay, lost the mouse. And Python is very bad at this. Because what the CPU does is to basically say, if I have data in this part of memory, then probably the next data is contiguous. It's close. And but in Python, if I have a simple list of persons, again, Alice and Bob, then what happens in memory is this kind of stuff. So the Python list is composed of 2 objects, and every object is a pointer to a person, and every field of the person is a pointer to a list, so it's to a string or to a number. So if I want to do the average of all the ages, I need to follow a lot of pointers. This is called pointer chasing. Like you start from here and you go there, cache misses probably, because it's somewhere else in memory. And then I follow these pointers, cache miss again. And then I read the next item on the list, which was in cache before, but I trust the cache to follow the pointer. So I need to follow them again. This is like horribly slow. And there is basically no good solution for fixing it in Python. I fear that as the language as we know it is, well, just cache unfriendly. There is not much we can do, even with crazy JIT compilers and anything like this. So from some point of view, the sad truth is that at some point we can make Python super fast. That there is a limit that Python cannot cross, unless we want to break some of the existing compatibility that we have. And I would like, I mean, it would be nice now we have some kind of announcement to say, but no, like, this is like... Maybe. No, okay, I mean, it would be nice if I have this crazy announcement. Yes, I found a way to optimize Python. It's not true. But I feel that basically, as a community, as a language, like, if we want to move forward and make Python, like, I would like to avoid this, like, rewrite everything in Rust. Like, I would like to be able to write my thing in Python and be as fast as Rust. How can we move forward? I think that the only way is to, like, basically tweaking the language semantics. We can keep the dynamic part, which are actually useful, but maybe design the rules in such a way that are easy to compile, and like in such a way that we can remove the abstraction overhead, and we can have a type system which is oriented at performance, because the current type system of Python is kind of a hack on top of the existing language design, and it's not really designed for being useful for compilers to produce fast code. And we should somehow find a way to remove this C Python overhead, because if I want to use C libraries, I would like to be able to call from Python without paying the cost of the C API. But most importantly, we should find a way to stay Pythonic and have the feeling that we all know is Python. And yeah, I'm working actually on a project which I call SPY, which stands for Static Python, but it's not, I mean, that's not the announcement. Like, it's not ready. It's with research, basically, work in progress. But basically, it's a language which kind of Python without the bad parts somehow, which try to fix all these problems and meet all the goals that I'm describing in this slide. I presented the SPY at PyCon 1 week ago. So if you follow this link, you can find the slides. And I think that in 1 month or 2 months, the video should be online. So it should be like, if you're interested, you can watch it. And while we are at it, another career advice, like, like documentation is super important. Do we agree, right? Yeah. Okay, I mean, sometimes I don't follow my advice because, like, this is documentation for SPY. Let's see, yeah, this is the README. How do I go back? No. Okay, so yeah, I think I'm done.
Thanks, Antonio. I think we have plenty of questions, and I think we have time for the Q&A session now. The first question, can I go ahead? Do you want to drink?
No, go ahead.
Wait. Okay. So, do you think a smaller standard library will make Python faster and more maintainable?
Removing the standard library?
A smaller.
No, I don't think so, because like the standard library, a part of it is just Python code, which could be just put somewhere else, but it doesn't make the life of the compiler any easier. Some of the standard library is written in C, but again, like, it's the same kind of C code that any C extension can write. So no, basically it doesn't make any difference.
So the second question is breaking compatibility in the 3 versus 4 compatibility is, we did it once. I mean, I think it's
3 versus 4?
I think it's Python 3. Yeah, I think it's 2 versus 3. Or
okay, can I read the question?
Yeah, because I don't know if the user is
no, okay. I think that this wants to say, okay, we are breaking the compatibility, so we are going towards the Python 4.
Oh, okay, yeah. So
like, and then
3 versus 4.
Because for those who are new in the community, 12 years ago or so, there was this 2 to 3 transition in which Python 3 broke the compatibility with Python 2, and it was a mess, and a lot of like problems in the community, took forever, nobody was happy, and that's something that the C Python code developers are very well aware. Guido in particular, like, he says very explicitly all the time that he doesn't want to do the same mistake again, and I agree. Like, the problem of the 2 to 3 conversion was that you had to do it all at once. Like, either your program runs on Python 2 or in Python 3. And you can't do any kind of incremental migration. What I have in plan for SPY is basically that you will be able to just write parts of your packages in SPY, for example, and still use normal Python for what you don't want to port. So, but what I'm doing is not Python 4 at all. It's a kind of external project.
Thank you.
You're welcome.
Okay, yeah, I just got an upvote on this question. So the first one now is another one. Any thoughts about Mojo language? So
it's not the first time that I hear this question, and I would like to understand, like, why do you ask about Mojo and not, well, Java or Go? I think that the counter answer to my question is, usually, because Mojo claims to be like a new Python, Python faster, and blah, blah, and I say it's a lie. I mean, not a lie in the sense that they want to be bad people or anything like that, but Mojo is not Python. Like, it's something that has a Python-compatible syntax somehow, but it's a completely different feeling. Like this what's happening here? This stay Pythonic is not true in Mojo. Like, Mojo is a language in which you need to take into account object ownership and things like this. Like, not Python. They claim to be that they will be compatible with Python eventually, but I don't see how, honestly. So yeah.
They said it's a superset of Python.
It's not.
All right, so any tricks from other languages to make it more cache-friendly?
Yes. So it's not really from other languages, but there is a community in which, especially in the game industry, in which they use what is called like data-oriented design, and basically, to be cache-friendly, you design your data structure in a way that, like, you put the data close together in memory, knowing how you will use it. So for example, instead of having a list of persons in which you have a name and then the age, a name and the age, you can structure your data in memory differently, so you have all the names together and all the ages together. And then if you want to do the average, then all your ages are together in memory, so it's very cache friendly and it's much faster. You can do these things in C++, you can do it in Rust. In Python, again, we don't have the tools. So this is actually something that I want to explore with Py, having kind of tools for playing with this design.
All right. Next one is, how do you feel about compiling code from Python to C using Cython? That works for about 15–20% of programs.
Yes. This is okay. What's happening now? What did I do?
There you go.
Okay. So with Cython, we are in this. We have two problems. The first is this one. Even if you compile with Cython, then you still have to, if you take Python code without type annotation and compile with Cython, Cython has to do this stuff. So it removes a bit of overhead for the interpreter, but not the big of it. You can apply type annotations, but then you are in strange. I've used it for a while to try to make a library super fast. And it's kind of hard because if you're just happy with some result, yes, it kind of works. But then if you want to like have super fast, then you need to know exactly what Cython is doing. And then you change a line, you forget a variable annotation, the code still works, then it goes to the slow path. And so you are in another problem, which is this one, basically. And so yes, it works somehow, but I don't think it solves all the problem. And it's super cool piece of I mean, I don't want to sound too negative. Like all the project I'm talking about, CPython, JIT compiler, Cython, even Mojo, all super cool technologies, and thanks to all the people that work on it. Like I don't want to be like the one who wants to tell everybody how to write software. Like, not at all. But each of these has limitations. Basically, that's what I'm saying.
Thank you. What about releasing the global interpreter lock?
This is a completely different topic, which I didn't cover, and it's very important because for those who don't know, Python has historically had a problem with multi-threaded applications because it has what is called it used to have what is called a global interpreter lock, which means that even if you have multiple threads in Python, only one of them can run at each time. And in the modern hardware, you have a lot of cores and CPUs, and you cannot use all of them with Python. There were workarounds, multiprocessing, release GIL in C extension, etc., but it was not good. Now, recently, the CPython developers merged a pull request to remove the global interpreter lock optionally, and now it means that we will be able to have free threading in Python for real and have full Python application. It's cool. It will make it possible to use multiple threads, but for every single thread, you still have the same problem that I'm describing. So The problem that I was describing in this talk are kind of single-threaded problems. And with multi-threaded, yes, you can use multiple cores, but you still have this kind of abstraction over rare and dynamicity. The other problem is that I predict a lot of segfaults. Like all the libraries, they were, all the C extensions in Python, they were written knowing, or maybe taking into account, or maybe not even taking into account explicitly, but in practice they had a GIL. And it worked, and if you just suddenly remove it, well, they need to fix their code, probably. So that's why it's experimental. You need to enable it at compile time. It's basically not stable at all. It's just a giant experiment that you are doing as a community. I think eventually it will work and will be a good tool to have, but I don't think it magically solves all the problems.
Okay, thank you. You show us a very exoteric feature from Python that dramatically slow down the language. Do we really need them? Why, in your opinion, they exist?
Okay, well, that's like a kind of philosophical question. Do we need them? Yes. Like, some of them we don't need always, but there are cases in which we do. Okay, maybe deleting the attributes, the dunder add from the class, I never see it in real code. But adding attributes to the class dynamically, that's like methods to a class, that's something which I did. Changing the class of an object is something which I did. There are cases in which it's useful. But yeah, I mean, it's a trade-off. Again, I think that we should find a balance to keep the feature that we need and remove. And basically, it could be that this dynamic feature can happen very early in the program, and then we say, no, they are no longer allowed. So for example, meta classes are useful. With meta classes, you can have SQL alchemy, but they are very hard to optimize. But you can say that you can have meta classes when you import the module, and then after a while, they are no longer acceptable. Like they don't work. You cannot create new types at runtime. I think this is a very good balance because it gives you enough freedom to implement all the cool libraries that we want, but then it makes the life of the compiler easier. So this is one of the tweaks that I would like to try for making Python easier to compile, basically.
Thank you. I think we have time for another couple of questions because we started late, so we're going to recover that 5 minutes. So I think this is a funny one. So why you keep using type annotation in your code snippet in a presentation?
No real reason. Actually, I mean, well, when I wanted to show static types that don't work, but I needed them. And then it was like as a documentation mostly, but yeah.
Okay. Okay. Next one is, what was the biggest mistake you found in a Python application as debugging its performance? And what's the solution if you found one, and what we should definitely not do?
Oh, I'm not prepared to answer such a question. The biggest, I mean, some very strange stuff, I found them, and they were not actually mistakes, but for example, and that's a problem that PyPy had, and the new CPython JIT will have as well, is that existing programs are written with CPython in mind and with certain characteristics, and people, they're trying to optimize them for, like, you have a big project that has been going on for years, and you try to optimize it. You apply all the tricks to optimize for the Python that you have. And then you use new techniques, and then the performance characteristics are completely different, and something that earlier it was innocent, now it becomes extremely expensive. So a real case that was a big problem in PyPy was, I think it was Django. It was created, like you had a function, and then inside the function you create a class and return it. And they were doing it like at every time you call the function. And in CPython, for the way it works, it's not really a big deal. But for PyPy, well, it assumed that the class is unique, and then every time you see a new one, then you have to throw away all the code. It was an incredible performance problem. What we did was to, well, put the class definition outside the function, and everything was fast. I mean, I don't think it was their fault, because when they wrote it, it was perfectly fine code, but stuff like this happened.
Thank you. Last question, and then maybe you can reach out to Antonio outside and asking for more questions. How does PyPy work with compiled extension modules?
Oh, that's basically another talk. Like I have 1 hour. PyPy works with C extensions by basically pretending to be CPython. The protocol to have Python and C to talk is what's called the C API, and it assumes a lot of stuff. It assumes that objects in memory are laid out in a certain precise way, which is the way CPython is using, and C extension knows how to deal with it. But for PyPy, we wanted to be faster. We had a garbage collector, different than CPython, and a lot of other stuff, so our layout in memory is different. So what we need to do is kind of emulate all the internal details of CPython so that we can, from the point of view of C extension, we look like CPython. But all of this is incredibly costly. There is a post by me, which I wrote on the PyPy blog 5-6 years ago, which actually goes into gory details of internals and why it is actually a problem, what we do to emulate reference counting and all the stuff, but everything is incredibly slow, but it works. And again, CPython will have the same problem when they will try to do more exotic stuff, I think.
Okay, thank you, Antonio. Thank you again. Okay, I think the coffee break already started, but you have plenty of time to get a coffee now.
Needs to like not. Oh. Is that okay?
It's weird. Sorry.
Yeah? Is it all right that it's touching my cheek? I just worry it would. It is a little bit. See? Yeah? Yeah, yeah.
Okay. Thank you everyone for coming. Let me just remind you first that the preferred way of asking the questions is a Slido, so you can ask them and upload them there. You can find the link on the website. And it's my honor to present you here David. He comes from Kraken Tech from London, and he's going to talk about crabs and snake, that is Rust and Python. The stage is yours.
Hello, everyone. So, who here has written a program in Python? Oh. I love Python. You can be really productive in it. It's a very high-level language, and it kind of doesn't force you to think about all these details of what the computer's actually doing. You don't need to think about memory management or anything like this. You can focus on writing the business rules of your program. That's why we're all here, isn't it? It's great. But, as you may have heard in the keynote, it's also kind of slow. You can't do things across threads very easily because of the GIL. And there's a lot of overhead to all the dynamic features of Python. And so you can think of Python a little bit like a friendly tortoise. You can have a very nice relationship with it, but it's ultimately limited in the speed of its runtime. Now, who here has met this person, Ferris the crab? Who has programmed in Rust? Less people. Not surprising. So Rust, I also love Rust, though I haven't used it very much. And it's a really different kind of language. It's a much lower level language, and it gives you a lot more control over what's actually happening in your computer, and in particular, the memory. But it's kind of hard, to be honest. And so you can think of Rust like a cheetah. It's the fastest thing on land, but it's fierce. And when we choose the programming languages in which we write our programs, we're making trade-offs, aren't we? You know, sometimes we want a friendly tortoise, sometimes we want a cheetah. Sometimes we want to optimize for being really productive as a developer, and not having to think too much about like computer details. And sometimes we just want raw speed. And it's a shame that we have to make these trade-offs, but maybe we don't. Maybe, well, we can. We can have both within the same program, because Python and Rust can interoperate. And so this talk is about like an introduction to how to do this. I did this in my open source library GRIMP, which is a static analysis library which is used by Import Linter, which is another of my projects, which you might a bit more well known. And what Import Linter does is it analyzes all of the imports between modules in a Python package. And you can write rules, which are called contracts, to check that you're following certain rules. So it's an architectural linter for Python. And we use this at Kraken. Kraken has a rather mind-boggling 60,000 Python modules in our monolith. And so we need to do things to stop it getting in a mess. And so we write lots of contracts and run them in import linter in CI to check that we're not introducing dependency cycles and things like that. This is just one example of one contract that was running in CI. It was taking over 6 minutes a few months ago. And so I wanted to try and find a way of making it faster. I wanted it to be more like a cheetah. And so I experimented for the first time with writing a Rust-compiled extension module within GRIMP. And it was kind of like, I just focused on the really hot path, the path that sort of is quite a small bit of GRIMP that I wanted, where most of the time is being taken. And it was a straight rewrite, really. I didn't do anything different algorithmically. And I got 6 times speed up, which is great. But I think this is just the beginning. I haven't even done any concurrency, even though, you know, the GIL's not there anymore. And some people say, you know, depending on your use case, you can potentially get it to be 1,000 times faster. So it really is amazing what you can potentially achieve with speed if you can put Rust inside your Python packages. So I actually am quite bad at Rust. I don't understand loads of it. I'm very confused by it still. I was able to get this working, but I'm very much at the beginning of my journey in Rust. And you know, I encourage you to like have a look at it. Try not to be too intimidated by it. You can achieve this kind of thing, even if you're a newbie like me. But what I found particularly confusing was to try to do this, I had lots of different things to learn, different tooling, a whole new language, also like just the concept of 2 languages interoperating. And I was pretty confused and didn't really have the foundations conceptually of how to do it. So what I want to do in this talk is give you the conceptual foundations of the tooling that I used. So we're sort of going to spend a little bit of time with this diagram. By the end, you'll understand what's going on and the different roles and responsibilities of each bit. But we're going to start with this. So it's Python calling into an extension module. Python supports native extensions. And so if you type import foo, we all know this probably, it's going to look on the Python path for a Python module, foo.py, expecting to find some Python in there. But it's also going to look for a file called foo.so. That stands for shared object. And this is a dynamic library. It's compiled binary, and it's going to try and interact with that as well. So let's give it a try. Let's just create an empty dynamic library file and see what happens if we try and import it. What's going to happen? That's interesting. So you can see straight away Python is trying to interact with this file. We're getting a DL open error. I think that stands for dynamic library open. And this is because the dynamic library isn't well formed, it's just an empty file. So let's use Rust to compile a well-formed dynamic library. It's going to be empty, it's not going to do anything, but it's going to be well-formed, and see what happens now. So what we're going to do is we're going to focus on this next bit, and we're going to simplify it. We're just going to use the Rust compiler directly. Rust-C is the Rust compiler, and you see that this sits within something called a Rust-up toolchain. So the way we're going to get Rust on our computer is to install something called Rust-up, and then we're going to use Rust-C to compile the extension module. So Rust-up is a toolchain multiplexer, which I think is a good name. And it allows you to have multiple toolchains on your system at once. So it's something you install on your local computer at system level, and it's going to give you, within a toolchain, the compiler, Rust-C, and Cargo, the package manager. But you can have other toolchains on your system as well and flip between them. If you've used pyenv, it's sort of doing something like that, but for Rust, although other stuff as well. And you might use Rust-up to, say, upgrade your version of Rust on your computer. But anyway, if you install Rust-up, that's your first entry point into Rust. you will have Rust-C and cargo available on your command line. So let's now create our first Rust file. .rs, that's the file extension for Rust. And you can see it's really easy Rust if you don't write any. And then we're going to compile it. So now we've got our compiled, well-formed dynamic library. What's going to happen if we import this? Well, it's still an error, but it's a different error. Dynamic module does not define module export function pyinit foo. So what's happening is Python is expecting to call some kind of function inside this dynamic library. And these dynamic libraries, they do have a kind of structure. I just found this one lying around on my computer. And there's a tool called nm that you can run, and it will show you all the entry points into the dynamic library. So this is some of them. And so what's happening is Python, particularly CPython, is expecting some kind of interface that it can interact with this dynamic library so that it can interoperate. So how do we find out what? If you go to the CPython docs, there's a whole page on this of how to extend Python with C or C++. But actually, it's sort of about more than just C or C++. Actually, you can write it in other languages like Rust and compile it. And if it's conforming to the same interface, CPython will still be able to interact with it. Fortunately, we don't need to read all this very big, long page with lots of C boilerplate because we're doing it in Rust, and there's a really good library in Rust that makes it a lot easier. It's called Pyo3. So in Rust, libraries or packages are called crates. And you see this is on a website called crates.io, and that's the equivalent of PyPI for Rust. So we're going to use Pyo3, and this is really like the sort of secret sauce of this whole thing. I'm incredibly impressed with Pyo3. Like, I can't believe how well it seems to have been designed. What we're going to do now is instead of using Rust compiler directly, we're going to use cargo, which is a layer on top. And that's going to handle things like using external dependencies. It's also going to give us a project framework for our source code files. So we're going to install Pyo3 inside it, and then we're going to write the source code. And then we're going to run this command called cargo build. And that's like the layer up on top of Rust-C. So we've got cargo because we installed Rust up. Cargo new lib rusty. I'm going to call this package rusty. And it's created a couple of files like this. This is the structure on my computer. It's come with a project config, cargo.toml. This is a little bit like pyproject.toml if you've used that. And then a place to put our source code, lib.rs. So I'm going to make a few changes to this, but don't worry about the details. It's just to give you a bit of a flavor of what you need to do. And eventually you'll probably do something different as we build more layers up. So the first thing I'm going to do is I'm going to edit cargo.toml. And I'm not going to show you this, but basically I just put in like a bit of configuration, including the version of Pyo3 that I'm going to use. And cargo is going to know to fetch that from crates.io. I'm also going to add this file. This is called build.rs, and it's just used in the build process, but it's just some boilerplate that Pyo3 told me to include. And finally, this is the source code that we're going to compile. And this is what it is. This is our first Rust. Oh, look. All you really need to know about this is it's a function. It's called Rusty. Ignore all the other stuff around it, except that bit in yellow. That is something that Pyo3 is providing us. It's an annotation. We're saying this function corresponds to a Python module called Rusty. So this code is all we need to build something that is an empty Python module, or apparently a Python module, but actually compiled. So the command we use now is not Rust-C, but cargo build, this layer on top that compiles it. And then we're suddenly going to have lots more files on our computer. And the one I'm interested in is this one at the bottom, librusty.dylib. If you use Linux or Windows, it might be a different name, but this is a Mac. But this actually is that dynamic library. It's just got a different name. It's got the wrong name. It's not going to work if it's called this. It's also in the wrong place. So I could just create a symlink here to point to that file, and I'll give it the right name, rusty.so. So if I spin up a Python REPL in that same working directory, then I should be able to import it. Let's try. Import Rusty. What's going to happen? Yeah, no errors this time. It doesn't do anything yet, but, you know, I mean, it's not very useful yet, but we got somewhere here. Now, I'm going to return to the whole like making some functions that actually do something in a minute, but we need to finish this sort of tooling bit first. So, pip install grimp. That's my open source library. It used to be Python, but now it's got some Rust in. We don't want people to have to download cargo and create some symlinks and things whenever they pip install grimp. We just want to type pip install grimp and like not have to worry about it. So this is where the other side of the picture comes in, which is maturing. So we've now got our Python virtual environment with our Python application code in, and we're also going to pip install maturing. And we're going to use maturing as an additional layer on top of cargo, which is on top of Rust-C. And like our development workflow is whenever we change the extension module code, we're going to type maturing develop. And that's going to do cargo build, but it's also going to do a little bit of other stuff. So let's install it into our virtual environment, and then we're going to reorganize the code a little bit. I'm sort of assuming that we've got a pre-existing Python project that we want to add the Rust to. So there's different ways you can do it, but like this might be one way where you have Python and Rust in separate folders. But we've got our pyproject.toml, and that's the important bit, because that's what pip install, that's what pip is going to look at. And in particular, oh yeah, notice we don't need that build.rs anymore. Maturing is going to do that for us, so a bit less to think about. So this is our pyproject.toml, and the important bit is this bit. What we're doing here is when you normally do pip install, it's going to use setup tools. But it's actually pluggable, the build system. So you can say, well, I want you to do something different. I want to hand off to another system to do the whole install process. And so we're handing it off to maturing instead of setup tools. So let's type maturing develop and see what happens. So there's going to be various things. Notice it's building a wheel. We'll come back to that in a minute. And now there are some more files. It's compiled our Rust code, and it's notice that shared object file there. It's actually put it with the right name. It's a bit of a longer name, but it'll still work in the right place based on our configuration. So this will now just work without us needing to do any of that symlinking or anything, which is great. Well, it's great for me, isn't it? But it's not actually great for other people. What about the other developers who want to just pip install grimp? So this is a bit more of a challenge because when you compile code, it's different from an interpreted language because it's machine code that gets fed directly to the CPU, and different CPUs speak different machine codes. And so you actually need to compile for different platforms and chipsets. To be honest, I don't even really understand it that well, but like, I think you might even need to compile it for different versions of Python. But you need different binaries depending on the environment in which it's running. So how do we manage this? If you go over to grimp on PyPI, look at a release and head on over to download files, you'll see a source distribution at the top, but you'll also see all these built distributions. And these are wheels. This is what a Python wheel is. And wheels are much more important once you start doing this kind of thing, because wheels contain built assets for a particular environment, a particular architecture. You know, you can these are a load for Linux. You know, it's saying this is for Python 3.10. on x86, 64 or whatever. And there are loads of these. There are about 50 different wheels for each GRIMP release. Now, this is the kind of thing that's a bit intimidating to me because I don't really understand anything about chipsets, really, or wouldn't even know what things to support. But this is the final bit of maturing, which is really nice. It's got this command called generate CI, and you give it the CI provider you're using. So in this case, I use GitHub Actions, and then it spits out the YAML configuration that GitHub is going to look at to do the release. So you can just redirect it to a YAML file, and then it gives it all for you. Now, when I do a release from GitHub, it's going to build 30 Linux wheels, 10 macOS wheels, 10 Windows wheels, and the source distribution. If they all work, then it's going to release it to PyPI. Isn't that lovely? So this is the whole kind of picture of tooling. Just to sort of recap, you're going to install Rust app, and then you're going to get your Rust C and your cargo in your tool chain. You're going to create a cargo project maybe, and then you're going to install Pyo3 in there. And then in Python, you're going to have maturing as an installed package, and that's going to be like the orchestration layer for building everything, and your main command is going to be maturing develop to make sure you compile things. So it's time now to actually do something with a function. Let's implement this Python function in Rust. It adds 1 to an integer, and it's pretty similar, actually. It's quite readable. The main difference is that I32, which is what's being passed in, and that stands for a signed 32-bit integer. Interesting, that's already a bit of a lower level concept, isn't it, than just an integer from Python's perspective. So this is the source code, not very much of it. We've put our function in there, and then we've annotated it with this PyFunction annotation. And then there's just a little bit of boilerplate here where we add it to the module. And this is enough to tell Python, sorry, I'm standing in the way, to tell Pyo3 what to build. So mature and develop, remember that's how we compile things. Let's see what it happens. We should now be able to call this function in that module. We should be able to add 1 to 10. What's going to happen? Look at that. You couldn't do that with Python, could you? Do you know what this is? Crabs and snakes. Okay. I'm going to close with a little wake-up call, because I said Rust was fierce. What happens if we add 1 to this number? Can anyone see what's special about that number? 2 to the power of 31. And signed 32-bit integers don't go up to 2 to the power of 31. They go up 1 less than that, because there isn't enough information in 32 bits. So what's going to happen when we add 1 to this integer? We're going to get an exception, overflow error. That's interesting, isn't it? It's interesting in a few ways. Like, for a start, it's a reminder that, like, integers, you can think about integers in quite a few different ways, and really a Python integer is a very high-level idea of an integer compared to a Rust integer, potentially. But also, Rust doesn't support exceptions, so how do we get an exception? That's clever, that's nice, isn't it? It didn't just explode, it actually works nicely with Python. And okay, maybe we'd need to put some validation in at the Python layer to make sure we don't call these or whatever. You've got more context in your program, but it's nice that it feels like Python. So this is my mental model of what's going on, and the reason why I'm talking, it seems a bit random why I'm talking through this particular bit, but this was the bit that I found most confusing and wrong-footed me. I didn't really just understand what was happening across the boundary. So you've got your Python integer, that's a Python type. Then you've got the types that Pyo3 defines. And these are in Rust, but they're also kind of Python. Pylong actually is the same it's the same data. It's the same data in memory. It's just expressed in Python instead of, expressed in Rust instead of in Python. So if you pass in an integer, Rust can actually just get that same memory, and it will interact with it with a pi-long. But it's quite a heavyweight object. It comes with like ideas like the GIL and things that make it harder to work in a fast way with. You know, and there's lots of, as you saw in the keynote earlier, you know, there's a lot of heaviness to Python objects. And what I did is I used a lower level Rust type. Now what happened is it wasn't passed in as a Rust type just directly. Pyo3 is looking at runtime at it, and it's converting it based on the type signatures you choose. So you can choose lots of different type signatures for all these different things, and Pyo3 is responsible for doing the conversion, and then if it can't convert it, raising it as an exception. So like, I think it's worth like bearing this in mind when you write your extension modules. Final thing I'm going to say is, I wanted to have a bit more of a longer section on this, but there just wasn't time. Like, Rust is incredibly confusing, and it's really hard. Like, the error messages you get are like nothing you've ever seen, and it like you can't bluff your way very easily because it won't even compile. You have to. I don't think you can bluff Rust very much. You actually have to learn it. You have to learn it in depth, but it's going to really change the way you think about computers. Well, it has for me anyway. And there's lots of good resources. One that I would recommend is just go on the Rust website, go onto the Learn tab, and then there's a free book called the Rust Programming Language, which is really, really brilliantly written and deep book that I'm reading at the moment. So I recommend having a look at that. So, in conclusion, we can have our little tortoise, friendly little tortoise, for all that lovely dynamic code where we can work quickly, that's really accessible to lots of developers, but maybe there's just a few places in our programs where we need speed of runtime. And we can have both of those together. We can have crabs in snakes. Thank you.
Thank you very much for this amazing speech. So we have a few questions. Is it possible to pass classes as arguments to these Rust modules? Do we have the right person, the class in both Py and RS file?
Yeah, so from what I understand, the question is, you know, like, are classes supported essentially? And the answer is yes. Like, loads of stuff is supported. You can do classes. You can define a class with Pyo3 that will feel like a Python class. There might be some restrictions on it, but absolutely. You can even do things like logging to the Python logger from your Rust code. So it's quite amazing what sort of interoperability there are. And I think it comes down fundamentally to the CPython spec, which sort of allows you to, like, it's designed so that you can actually write a lot of C-based lower-level stuff, and then everything is supported within the higher-level Python stuff. It even works on PyPy. I tried that. I actually asked the question in the keynote about how does that work, you know, and his answer was, well, it works, but it's incredibly slow. So maybe do some research if you're going to try and do this and run it in PyPy. Might not get the right results, but it does work.
Thank you. And Arthur asks, how would you approach testing such a two-language piece of code?
Yeah, that's a good question about testing. So you can, Rust has got a good testing ecosystem as well. So you can write tests just of your Rust code, or you could write tests at of your Python code calling into Rust. The approach I've taken with Grimp is that I had a load of tests already that were in Python, and I treated the Rust code as private, you know, an implementation detail, so that I didn't write loads of Rust tests. But if I'm honest, I think probably I should have written more. I do try to do TDD, and I think you probably it's worth writing lower level Rust tests, particularly if you're new to it, because It can be hard to track down the bugs and things if you're testing at too high a level. You could always delete those tests afterwards in Rust, but I think I would probably have both of them. Yeah, I should say as well, like, this is open source. You can go and have a look at GRIMP and what I've done. It might not be best practice. If you want best practice, probably look at the Pydantic core source code, which is, you know, or ask Samuel, who I think is at this conference, about how to do that.
Thank you very much. Unfortunately, we are out of time, so I suggest approaching David after the talk. Thank you.
Ah, si può allungare, sì, meglio. No, assolutamente no. Yes, I will. No, I don't think it's necessary. I have time up to 45 minutes, right?
Yeah,
and
you can divide it however you
yeah,
want.
whatever remains is going to be the Q&A.
Yeah,
Yeah, it's going to be fine. Oh, Loris Croc. Yeah, whatever comes out, it's fine though. Don't worry. Oh, oh, you do? Oh, you're asking me if I had one. Oh God, no, I don't really. Well, I do have a question maybe. So we're waiting for 3 more minutes, right? Okay. So a question: who here has?
You can ask the questions on Slido. It's the preferred way to ask. Here we're having Loris Croc. He's the Vice President of Community at Zig Software Foundation. And he's going to talk about what would happen if we didn't have to bundle binaries into Python packages anymore.
Thank you. Okay, hello everybody. So I'm going to introduce myself more in a moment, but first I want to show you what we're going to talk about in this talk so that you can manage your expectations. So first of all, sorry, my preview is a little bit small. So we're going to look at why and how Python uses low-level programming languages, which I think is going to be more interesting for novice Python users. Considering the amount of hands that were raised when I asked how many people have written C++ code, I'm going to go fast on this part because I think most people are already up to speed with that. Then we're going to talk about how that interoperability with lower level programming languages impacts the creation and usage of Python packages. And then which is going to be more interesting for more experienced Python users. And then I'm going to look at some Python package index stats, just a couple, and discuss some potential future ideas for Python packages. And I think this last point is going to be especially interesting if you see yourself as a Python community member. So not just a voiceless, anonymous user of the Python language, but also somebody who is part of the community discourse and maybe who can, I don't know, even influence it a little bit. So yeah, my name is Loris Crow. I'm VP of Community at the Zig Software Foundation. And I have a small YouTube channel. I also live code on Twitch. So if you're interested in seeing somebody write some Zig code, check me out on Twitch. I will probably, once I come back from PyCon, I will probably go back to writing my own static site generator. I have opinions, especially about templating languages. So I'll go do that. And lastly, I also organize a conference in Milan called Software You Can Love. We had one a few weeks ago, and hopefully we're going to have another one next year. So,
Just last week, though.
Oh, last week. Oh, yeah. Anyway. Anyway, some disclaimers. So I have written a bunch of Python. I've started using Python in university. My coursework was in Java. I didn't care. I did mine in Python anyway, and it was a huge productivity hack. My first paid job was in Python. It was like a Django application. So I've done a bunch of Python. Also, I did bioinformatics afterwards, some more Python. But then life happened, and I parted ways with Python. So I have some experience with Python. Also, this awesome T-shirt that I have, duck typing. As you can see, there's also a banana peel. This one comes from a PyCon in South Africa. But I am bringing to you like a bit of an outside perspective. I am part of the Z community. I know of some things that we've done, and I'm kind of like bringing you gifts in a sense. And that means also that it's up to you to decide if you like these gifts or not. So like I will make some statements, some claims, and ultimately, though, it is up to you to decide exactly how well they suit your use case or not. Lastly, despite the title, this is not a critique of the wheel package format. I know that it's like Python wheels are like zip files, they have an internal structure, etc., but I'm not going to critique that. This is more high level. So why does Python rely on low-level programming languages? Usually people say, well, because Python is slow. There has been a keynote also explaining about exactly how, to what degree that is true or not, etc. But I don't like it as an answer because I feel like it's imprecise and also like feels like a criticism. Like you say, oh, well, because it's slow. And I feel like we can do better. And I'll try to provide you with two reasons, in my opinion, why Python relies on lower level code and on lower level programming languages. And the first one is because Python targets a virtual machine, not the hardware. So when you write Python code, you're pulling levers inside of a virtual machine, and the language syntax makes it easy to do that. And it doesn't make it as easy to instead have precise control over the hardware, because the way Python is designed, you pull levers in the virtual machine, and then the virtual machine worries about making that happen on any specific piece of hardware. So that's nice, because that also means that in Python you can easily do things that otherwise would be hard to do if you only had like C, if you were writing C, some of which can be problematic, as the keynote showed. But yeah, the flip side is that whenever you need instead precise control over the hardware, then Python is not going to be particularly good at giving you that level of access. And that tends to be the case, especially when you care about performance, because performance means making sure that the machine does exactly what it has to do to perform the operation. And like, it's not just a matter of obtaining the right result. It's also how you do it also matters. The second reason it's connected to this one, like the second reason why Python relies on lower level programming languages, but in my opinion, it's distinct enough to deserve a separate bullet point. And that is that very sophisticated implementations of algorithms are written in low-level programming languages. Like there's a bunch of complicated, sophisticated libraries that have been implemented in C, and you want to reuse that. and so you have to be able to access that implementation. In theory, you could spend a bunch of effort and write this stuff in Python, but the reason why people use C and C++ and lower-level programming languages is because these languages act as a form of like lingua franca among other high-level programming languages. Like if you were to write this stuff in Python, like if you were to write like a super complicated matrix multiplication, image processing, whatever algorithm, you write it in Python, then only Python can use it. Well, in theory, other languages could spin up a Python VM, but like the whole point was performance, and now you're doing weird stuff to make it work. So it obviously makes more sense to write this stuff in C. So in a sense, it's a way of getting more mileage out of effort that other people have spent. And this is kind of like the same boat in which all high-level programming languages are. All high-level programming languages make it easy to do high-level stuff, not as easy to do low-level stuff, and they all then tend to rely on C and C++ mainly. But not only, there's also Rust, like in the previous talk, there's also NIM, and some others. Fortran, of course, also. In any case, so how does Python rely on low-level programming languages? The talk before also got into more details here. I'm just going to give you like a super high-level overview, but the idea is like if you're a package author, you use C types, CFFI, which is both the name of the concept of having a C foreign function interface system, and also the name of a package that actually offers that functionality in Python. And so that way your C, C++ code can interoperate with Python. The C, C++ code that you wrote has to be compiled to a dynamic library, and those dynamic libraries are machine code, so they are specific for the combination of OS and architecture that you have, and some more. We'll get into that in a moment. And then CPython, the interpreter, or actually whatever interpreter you have, loads that stuff at runtime. Different interpreters might have different rules, so not all interpreters can load dynamic libraries, or if they do, not necessarily the same way, but roughly speaking, that's how it works. And lastly, obviously, package authors also write Pythonic bindings so that their users don't have to deal with all the annoying lower-level C interoperability stuff. Great, this works. It's beautiful, it's perfect. End of my talk. No. No, it would be nice. Instead, welcome to C toolchain hell. Because if you were to make a package like this and you wanted your users to install it, well, now there's a few problems because they need a C, C++ compiler instead. If they don't have it, installation fails. Different platforms have wildly different setups, both in terms of the compiler itself, like all the major compilers, they all have quirks, but also their setups are very different. And that also adds complexity and jankiness to this process. Also, your users need build dependencies, and that is usually something that requires, basically makes your package depend also on other package managers. This is what happens whenever you have to install, like you do apt install lib this, lib that, or foo-dev, all these packages, these are all other dependencies. And so this thing is a mess. Also, these dependencies have dependencies of their own. Normally, the package manager deals with that, except when it doesn't. Then things get really funny for everybody except the user. So this is a problem. And so Python solved it using wheels. Python wheels to the rescue. So Python wheels can contain pre-built dynamic libraries. And this solves all the previous problems because users now get a pre-built binary. They don't have to build them themselves. They don't need build dependencies. They don't need C++ compiler. They don't have weird systems where things don't work for whatever reason. But wheels don't solve all problems because now you're distributing binaries, which thankfully is totally unexploitable. Can you imagine somebody exploiting a binary committed to a repo or something, like to add a backdoor to all SSH servers? Oh my God, that would be hilarious. Thankfully, it has never happened. But one day, who knows, it might happen. Then there's also other runtime dependencies. So the problem is, like, you're trying to avoid the complexity of C and C++. And as you try to escape, some of it still reaches and grabs you by the leg. Because your DLF, like your dynamic libraries, might depend on other dynamic libraries. And this is where tools like Audit Wheel come in, where basically they look at your dynamic library, look at other dynamic libraries that it references, and copies also those into your wheel. Has anybody here ever used Audit Wheel or similar tools? I see a couple of hands. thank you. You're doing a lot of work for everybody else, and they don't even know about it. But the thing is, like, the process is still complicated, and like there's some complexity that it's still bleeding through this system. You're trying to simplify the process, but some complexity bites back. And then there's another problem. For the people who were at the philosophy and software talk, Cartes, Descartes? I don't remember. Descartes was mentioned. Well, guess what? This is the Cartesian product of a bunch of sets. So to make pre-built binaries that work for everybody, you need to pre-build it for every CPU, every OS, every ABI. I'm not going to get into what ABIs are. Actually, people here already probably know. And there's also different Pythons. And these are like all the tag systems that the Python package manager uses to determine which is the correct wheel for each user. And so now you have to do ARM, Windows, ARM, Linux, ARM, Mac, Intel, Linux, Intel, Windows, Intel, Mac, et cetera, et cetera. And it's a lot. And then you have different versions of the OSs. Maybe Windows 10, Windows 11, not much of a difference. But man, whenever Mac updates, things break uncontrollably. And so you need to build a new set of wheels for a new version of macOS. And then there's Linux. So Linux has versions, but it doesn't just have versions. It has distributions. And every distribution is a beautiful snowflake, unique in its own way. And that means that your stuff compiled for Ubuntu Linux, it is not going to work on every other distro. It will work on some, but it will not work on others. NixOS, for example, is particularly funky from that aspect. So, and so this is when the many Linux tag was added. There's a PEP that adds it. Basically, many Linux, like you can use the many Linux tag to create a wheel that targets a subset of kernel, syscalls, and like other things that tries to be as compatible as possible with as many Linuxes as possible. Doesn't cover all of them, but it does cover some. And to build for many Linux, there's like VMs involved. So there's a bunch of complexity over there. But this is where I'm starting to kind of, I don't know, starting to be disappointed by this way of doing things, because we set out to do two things, right? Use other people's work, we are still succeeding, but also get performance out of it. And here we are starting to make some compromises, right? Because if you lose many Linux, you are like purposely cutting yourself off of improvements in the kernel. There are different versions of many Linux. Like I believe the one that is still mainly used today, I believe, I might be wrong, but I believe it cuts you off of IO ORing, which is like a set of syscalls that have been added to Linux that are actually improved performance of networking, file access, everything async related dramatically. And so for compatibility, you're cutting yourself off of all these improvements. CPUs, I mentioned Intel and ARM, 32-bit, 64-bit, but it doesn't end here, right? Because you also have CPU extensions. So for performance-sensitive code, having AVX, SSE, and all these other extensions for vectorized operations enabled does make a huge difference. And now you're also leaving that on the table. Or if you don't, now you have, I don't think that will actually support that, like the ability to select which flags your CPU has. So I don't think it works. But even if it did, now you have an even bigger combinatorial explosion of wheels that you have to create. So, and all of this is because the freaking C compilation toolchain sucks. And like, you're trying to solve it, but the problem is, if you could get reliable builds, then you wouldn't have to do all of this stuff in the first place, or at least it would be like a different picture. And this is where Zig comes in. So Zig is a compiler toolchain that not only can compile Zig, but it can also compile and cross-compile C and C++ code. I'll get to that in a bit. I just want to mention one thing first. I work at the Zig Software Foundation, so it's a 501c3 non-profit corporation, just like the Python Software Foundation. We don't have any big tech board member. We don't have any venture capital investment. I paid out of my own pocket to be here today. And my point is that for once, you're not looking at a startup product that is trying to get a quick exit, but we're actually here to try and improve the state of computing for real. So let's get back to the technology. So Zig, this is what we put on the website. Zig is a general purpose programming language and toolchain for maintaining robust, optimal, and reusable software. We do mean every single word in this sentence, but the one that is most interesting in this context is the one that says toolchain. So let me tell you about the toolchain. So first of all, the Z compiler can also cross-compile C and C++ code. And that is huge, especially cross-compilation. So if you take a C compiler or C++ compiler and you try to compile from Linux to Windows, out of the box, it's not going to work. If you try to compile from ARM to Intel or vice versa, it's not going to work out of the box. With Zig, you can. Not only with Zig code, but also with C and C++ code. You can target any platform from any platform, with some caveats, but it really works. And the reason why this works is that, for example, one thing that Zig does is that it bundles all the libcs, all the glibc. It also so glibc, Muscle, WASI-libc, also Windows, etc. And for glibc, it also bundles every single version of glibc. Maybe not the super old ones, but like the reasonably recent ones. They're all bundled, and so you can target a specific version of glibc, which maybe some people here understand when this is important, or rather have been bitten by what happens when you don't. And there's also a bunch of other tools that come with the Zig toolchain that help you with cross-compilation. And Zig is an in-place replacement for Clang. Like it's command line, it's flag compatible basically. So every time you invoke Clang, you can replace Clang with Zig CC, the CC subcommand, and it should work. And it's also not a separate compiler, just so we're clear. Zig bundles Clang, so you get the same compilation characteristics that you get from Clang, but there's also a lot of stuff built on top that does things that Clang cannot do out of the box. And I actually only mentioned some. There's a lot more. Another kind of important thing is that Zig doesn't rely on system-wide settings unless you want it to. So you can create, builds that are like consistent and reproducible, and not, oh, it only builds on my machine anymore. Also, Zig has a build subcommand, Zig build, which is a build system that can replace make, cmake, so you can also get rid of those dependencies. And it can also download dependencies. So the package manager can fetch and build dependencies for you. And this is all in a 40 megabyte dependency-free tarball. And it actually works. It's still work in progress. We're not V1.0. The language is still very in flux, but the tool chain is very solid. And for example, Uber is using it to compile their entire code base. Uber has a big Go monorepo, but they also have a ton of C dependencies. Some they wrote themselves, some are like usual open source stuff that they depend on. And C-Go can interface with C, but Go doesn't compile C code. It certainly doesn't cross-compile it either. So they basically were able to port their entire infrastructure to ARM by using Zig, and they still do today. There's like a Bazel packet, like a Bazel package that does this, that they developed. And yeah, this is awesome, and actually you can get the same power in Python. Pip install Ziglang, and it works. You get Zig. Let me read you the rationale for this. So, although Zig is useful in itself, the Zig toolchain includes a drop-in C and C++ compiler, ZigCC, based on Clang. Unlike Clang itself, ZigCC is standalone. It does not require additional development files to be installed to target any of the platforms it supports. Through ZigCC, Python code that generates C or C++ code can build it without any external dependencies. And this is how you make your build actually, portable in a sense. Then I said I wasn't going to trick you into writing Zig. I lied. If for any reason you also do some development, there is packages like ZiggyPyDAS, or more in general, we like to say in Zig that it's easier to use C libraries from Zig than it is from C. It's a bit of a strong claim, but if you catch me after the talk, I'll be happy to show you some evidence of that. So, in light of what you can do with Zig, here's the updated workflow. Use Zig in your setup.py to build your C, C++ Zig code. Zig can do also the fetching and the building of other build dependencies without relying on any system-wide setting. And so it's just Zig build. And actually, that's what I do. Like my static site generator, it's mostly Zig code. Well, actually, I'm not sure. It's certainly partly Zig code, but I also depend on tree-sitter for syntax highlighting. I depend on the CMark, markdown parser. These are C libraries. I don't care. I have the build script set up. I just do Zig build, and it works on any machine. And yeah, so one caveat of using Zig to manage your dependencies is that, well, those dependencies need to have been packaged for Zig. not every single C package out there has been bundled for or C++ have been packaged for Zig. So although there's a surprising amount of repositories that have like a build.zig file in them, but not all of them have them. But at the same time, in the Zig community, we have like an organization that we created called All Your Code Base, for those who know the meme, where we maintain our own build scripts so that people don't go annoy and harass the package maintainers to have them add a build script. So we do it ourselves. And yeah, lastly, those dependencies need to be distributable. If you don't, like, if the license says that you cannot redistribute them, then I mean, sucks to be you. Don't use proprietary software if you can. Well, congratulations, you do this, and your build is now consistent and optimized, because if your users download this and build it on their machine, if they have AVX or whatever instruction, then it's going to work on their machine. The executable will be able to leverage those instructions for better performance. And at that point, you can choose whether you want to offer pre-built wheels or not. Because my point is not that wheels should like go away and you should never pre-build binaries. Absolutely not. But there is a mentality shift from, oh, I have native dependencies, I must produce all the wheels, to now I can choose based on my specific situation. For example, the Ziglang package itself, spoilers, it's a wheel with a bunch of pre-built versions of Zig in it. Why? Because Zig depends on LLVM, so to compile Zig, you need to compile LLVM. That takes a bunch of gigs of RAM and like half an hour even on a decent computer. So yeah, no point in doing that. Let's distribute wheels. But not every single project that has native dependencies has the same situation. And actually, maybe so if you're thinking about big things like TensorFlow, you probably don't want to build TensorFlow on your machine when you install a package either. Fair. But you could have stuff like parsers that have like a native implementation of the parser logic, which can benefit greatly from vectorized operations. And that takes like a blink of an eye to build normally. So I'm suggesting you to add stuff to your setup.py script. And there's a real Python article about Python wheels, which I read, and I think it's fairly informative. I liked it. But there are a couple of claims in it. Oh, there's a bunch of claims in it about advantages that Python wheels have. I don't have an issue with most of them, but with a couple I do. So I would like to debunk them, because also I've seen them written elsewhere. So one says, wheels cut setup.py execution out of the equation. Installing from a source distribution runs whatever is contained in that project setup.py, as pointed out by PEP 427. This amounts to arbitrary code execution. Wheels avoid this altogether. Now, I'm not sure I understand the point here, because, like, sure, you don't run the setup.py, you're just running my binary blob that you have no idea what's inside. So I don't understand exactly the nature of this claim. Anyway, the second one is wheels are smaller than source distributions. For example, the 6th wheel is about 1/3 the size of the corresponding source distribution. The rest of the point is not super interesting. Now, this is another claim that I take issue with. So first of all, the example brought forward, the 6th wheel, if you click that link and you actually go take a look, the source distribution is bigger, sure, than the wheel, but it has documentation in it. So there's the source code and a bunch of docs, like 30 kilobytes unextracted worth of like RST files. And the wheel doesn't have it. And the difference in any case is like 30 kilobytes for the source distribution and 10 kilobytes for the binary wheel. So it's like a 20 kilobytes difference. And so the example, in my opinion, is comparing apples to oranges, so it's not relevant. But also the bigger claim that like a binary distribution is bigger than a source distribution, that is, I would say, that based on my experience, you cannot say this with in an absolute sense. Sometimes binaries are bigger than the source, sometimes they're not. It goes both ways. It's not as clear cut. But most importantly, I feel like this bullet point is absolutely misleading, because this is not a one-to-one situation. You don't have the source distribution and the wheel. You have the source distribution and a fan of wheels for all the platforms that you need to support. And that is actually shown really well if we look at a couple of stats from the Python package index. And the background could hint at what's going on there right now. So the Python package index is right now 85 terabytes big. And it's growing fast. So you can take a look. That is awesome. So congratulations. So the Python community is clearly very active and producing a lot of work. And actually, it's not going to, like, if you look at the growth, it's not going to take long to reach and surpass 100 terabytes. Great. But then if you look at the split, 3/4 of all that data is binary data. It's wheels. And it makes sense, right? I mean, you have to build all the freaking combinations of targets, platforms, etc. So it's what you would expect. So this should, in my opinion, finally debunk the real Python claim. But I also would like to add another couple of considerations about this. So first of all, disclaimer, I am not affiliated with the Python package index. I don't know anybody that works at the Python package index, or if I know them, I don't know that they do contribute to that. And I don't know their financials. But Python is a big community, it's one of the leading languages, so surely they're going to be fine financially. That said, those costs still exist. Like if you do some math and you look how much it's going to cost you to put 85 terabytes of data on S3, that is big numbers, right? We were trying to ballpark it. It's like 6 zeros, right? So big numbers. And the idea is, of course, there's going to be a bunch of big tech companies that are going to chip in. They're all going to be sponsors, participate. Assuming these things are actually on S3, AWS is most definitely going to give out a bunch of free credits to people. The problem is the costs. So for once, on one hand, the costs still exist. So if they didn't exist, all the same exact money could be moved somewhere else to solve some other problem that, or the thing that you would like to have improved. And the second point is that even if you're getting free money for this, man, it is very nice to be independent as an open source community. Every time a big tech does something that you don't like, if you're not financially dependent on them, you can speak up. You can say that they suck. You can speak your voice. If instead a big tech company does something that you don't like and you depend on them financially, then yeah, all you can do is stay silent and smile, because otherwise you're gonna get hit by the 6-0 AWS bill or whatever next month. So this is something that maybe it's not a pressing need, but it's not something that should be taken for granted, in my opinion, if you want to build a healthy community. And in the Zig community, for example, well, in the Zig project, we have the standard Zig Software Foundation offer for big techs and venture capital, where we say, sure, you can offer us how much money you want. What we're going to give you in exchange is 0% ownership of the organization and 0 board seats. Thank you very much. So when I say reinvent the wheel, here's what I'm trying to suggest you try out. First of all, try to perfect your source distributions using Zig. This is something you can do independently on your own today already. See how it works for you. Maybe it works, maybe it doesn't. Maybe you're going to hit like a bug, an issue, something that we haven't solved on our end. If so, maybe reach out, open an issue on our repository, talk with us. We're definitely interested in helping other languages solve their toolchain problems. Another thing as a user is maybe consider preferring a source distribution over a wheel if the build times are worth it. So if it's not TensorFlow, if it's not something that takes forever to build, and you suspect you will get some mileage out of having extensions enabled or some other thing specific to your specific machine, do it. Beware though that there's like all these CIs that run on containers. You start with a base image. First thing you do is pip install a bunch of packages. Beware that if you do this and you put all the extra flags to prefer the source distribution, so to compile stuff over installing the binary, that's going to slow down your CI. So you should cache that layer of your CI. Be smart. I would micro rent. That is also consider doing that anyway, because it can be annoying for projects having CIs keep downloading stuff forever. We, as the Zig project, we have people that start downloading Zig a lot, and we're starting to have like a build that we went past our free tier of S3 a while ago, and we also got tired of kissing ass to AWS people to get free credits from them a while ago, so it's a bill that we have to pay. And we know that a bunch of those downloads do come from just CI downloading Zig over and over and over and over. So be mindful of that. For people who are involved with the Python package index, here's an idea. Do evaluate if and when to add a cache package model. The idea is this. Today, if you delete wheels, it's a problem because you're not gonna, even though you might have the source distribution, it's not trivial to get from the source distribution to the built wheel. But if you make it trivial, like if you can make it consistent, like one command and it always succeeds at building for whatever target, then your wheels stop being data that you lose, well, that if you delete, you lose data, and instead become like a cached artifact that you can delete at will, and you could even decide that you're gonna allocate, I don't know, 50 terabytes or whatever memory to cache the most commonly used wheels, well, source distributions that have like a build step, like a C compilation step, and not the rest. And like you get a lot more flexibility. And this is how other package systems work. For example, Nix. The Nix package manager, you tend to build things from source, but there's a Nix cache system that basically allows you to speed up if you're building something that has already been built by a bunch of other people. And that's good. And more generally, so I used to have in the original draft of this talk, I had like a pretty lengthy rant about containers. I cut it, but I have some remnants. So my point when I say they invent the wheel is try to improve the state of Python packaging by embracing advances in systems programming and not by just saying, oh, there's this problem, I'm just going to slap a container on it. Because I feel like that solves the problem somewhat short term, but it's not a real solution. I even have a video for this. Let's see if it loads. It does. Right. Oh, no. My C toolchain is crap. Let's put Docker on it. Problem solved. Thank you very much.
Thank you very much. This was amazing. So, distributing the Zig compiler as a wheel is nice, but it is still disturbing a binary blob. Distributing a binary blob. If Zig gets compromised, a lot of packages would be infected.
Yeah, absolutely. 100% you're going to get pwned. Sure. Still, it's better to have one. It's still better to have one point of failure than have every single package you install be affected by the same issue. That said, it's a minor bullet point. Like if it was only a security problem, I don't know, I wouldn't have bothered with this talk, to be honest. I feel like the actual problems of having the communities shoulder costs that maybe they could avoid and getting actually the performance that you should get out of all the effort that you have to go through to get to be able to depend on lower level programming languages, I think that is more important and the main reason why I'm here today.
Thank you. And another question, what about Cosmopolitan?
I don't know, can you actually build, has anybody ever built a wheel that uses Cosmopolitan libc and can actually do fancy stuff with it? I don't see any hands. So Cosmopolitan libc is an interesting libc that does some clever tricks to basically create one executable, and that same executable can be run on different systems, even different CPUs. It's mind-blowing. But I would say it's a very clever trick, but I think it has some, it offers some things that are still a little bit brittle and problematic once you're just trying to get stuff to work. But it is cool, but we don't bundle it today, maybe in the future.
Would the thesis of this talk, switching to portable build systems to avoid shipping binaries, have been possible without Zig leaving the LLVM ecosystem?
So this is a reference to the fact that we today are depending on LLVM. So if you want to compile Zig, you have to compile LLVM first, and we want to stop doing that. The way this is going to work is that we're not ejecting ourselves forever from the LLVM ecosystem, goodbye, and make our own compiler from scratch, and that's it. But what we're going to do instead is work on our alternative, but still be able to use LLVM through the Zig package manager. So instead of having LLVM bundled inside of the Zig executable, what you're going to do is have Zig produce LLVM bytecode, and then invoke LLVM, like get LLVM as a package, and feed the LLVM bytecode to LLVM to obtain an optimized executable. So long story short, nothing is going to change for the end user. It's just going to be, it's just going to work in a slightly different way in the internals.
So there's this question, how far is Zig from getting rid of LLVM, and more importantly, where I can buy the tool at the end to avoid cleaning the dishes?
So the tool at the end, I think you can go to, I don't know, docker.com. As for Zig getting rid of LLVM, as I explained, we have a transition plan. We're not trying to just nuke LLVM and renounce or like say no to all the benefits that we get from LLVM. We are working on it. We are right now very close to the point where we're going to be able to do debug builds of Zig programs without invoking LLVM. Very, very close. Not for every platform yet. For, I believe it's going to be, the first platform is going to be like x86-64 Linux. That's going to be the first one. The next ones, the other ones are going to come next. But that is the closest milestone right now. So we're going to do it first for debug builds so that you can have instant debug builds, because right now, rebuilding Zig programs takes a while, and most of the time is spent in LLVM, which is fine if you're optimizing, but it's not fine if you're making a debug build. And so we're aiming for like very fast debug builds right now, and then we're going to do incremental compilation. Right now, Zig builds everything. Zig, not C. C has different compilation units, but the Zig code has one compilation unit that and everything gets rebuilt every single time. There's no extra granularity. We're going to do full incremental at the single top-level declaration level, and that's going to ideally net us pretty much instant rebuilds for arbitrarily large projects. It's pretty cool.
Is there a way to know in probably in advance, how big is the gain in terms of switch to Zig build toolchain?
In terms of like jankiness, humongous. Like the amount of jankiness that you get rid of. In terms of like performance, as in like how much performance gain you're getting from like building on the user machine versus downloading a pre-built wheel, it wildly depends on the application. And I would actually say probably for most people, it is not going to be that interesting. But for some people, it will be dramatically so. It really depends on the use case.
How far is Zig from 1.0?
5 years from now. That's what we used to say also 2-3 years ago. It's going to be a while. But Zig is going to be interesting for people even before it reaches 1.0. So don't get baited by the number. The number is just a number. Zig is going to wait. It's going to have like a slow rise to 1.0. We're going to wait a while before we tag 1.0. So it's not going to be a rush. It's more going to be like similar to Go, for example, where they waited a while before tagging 1.0, while Rust instead did it pretty early, and then they have a way of maintaining retrocompatibility. In our case, we kind of want to target 1.0 once we're really done with the language. So you will totally find a usable language, very stable, production ready, way before we hit 1.0. So like, look at the features, follow the development. Don't look at the number. The number doesn't tell you a full story. It's like it's just 2 digits or something like that.
Okay, a bit more general question. What will developer users experience if we don't distribute wheels and they don't have Zig on their computers?
Well, the point is that you put Zig as a build dependency. So like you use Zig-lang, the Python package, in your build script. So for them, it's still going to be pip install foo, pip install whatever you're building. So they don't need to have it installed on their own. The whole point is that this whole thing can be made self-contained through the Python package manager.
C is complex due to its diversity in ecosystem. Does Zig solve that? What are the caveats?
So C is very complex for its diversity. Well, so for what I presented in this talk, we're not getting rid of C, right? We're keeping it. So what Zig does is try to help streamline some, in my opinion, bad decisions that have been done in the past in terms of C++ toolchain that were never fixed, like defaulting on depending on everything on the system. I think that's a lesson that also Python itself learned, right? From going from like system-wide installation and everything to virtual environments, etc. That's the main one. As for Zig, the programming language, if we imagine that you're using a C library from the Zig programming language, or you're writing your own C application, there are quite a few language features that help with that. My personal favorite is alignment. I'll just mention one, alignment. Alignment exists, it doesn't matter all that much on big PCs, but like on the meta devices, it does matter more. And boy, do I hate, like when I was learning this stuff, I hated it in C. You don't see it almost anywhere. It exists, but it's not nowhere. Alignment, memory alignment.
You have
Oh,
to be,
Jesus.
your memory addresses have to be aligned to a certain system.
Yeah.
No, to certain bytes. So you can be aligned to 1 byte, to 2 bytes, to 4 bytes.
Yeah.
It depends on the
So
data.
some instructions expect your data to have to have the address that you pass to the instruction to be a multiple of a certain number. If that's not the case, like if you put your data in weird places, then either the instruction is not going to work, or it's going to have to fall back to a slower implementation. And this, as I said, this can, and sometimes it doesn't even work. Like for some architectures, you straight up get an exception, like a CPU exception. In Zig, alignment is part of the type system, and it's awesome. Now I can understand it, now I can make sense of it. There are plenty of things like this in Zig compared to C and C++.
Antonio this morning during the keynote was talking about alignment somehow, right? I think we was talking like data-driven design.
Yeah, data-oriented design. Alignment does come into play there because what you do there, what you do with data-oriented design is like you try to pack things together, and alignment can also feature into that. Yes.
No more questions online. Does someone want to ask, like live?
Can you say something about reproducible builds on Zig?
Yeah, so I don't believe that right now Zig is capable of making fully reproducible builds. I do think this is absolutely in scope. So I cannot make any promise on the state of today tooling, but yeah, we do care about this. So I mentioned consistent. I wanted to say reproducible, but yeah, we're not quite there yet. Oh, I have no idea, actually. Yeah.
Just wanted to add a quick note about the build time dependencies. So if you use pyproject.toml, there is this build section table. So if you use Zig to compile like a custom setup of Py file or something, you add Zigland or something in the build section. So when you pip install stuff, it goes through the PyProject and it sees that it needs to install Zigland, but it is not part of your library's dependencies, just at build time. So if it would be installed in a specific environment just to compile the code on your machine, and then that's okay. So your user do not need to depend on Zigland, nor your packages is made bigger just because it needs that.
Thank you. Okay.
Just a curiosity, because I don't know that much about Zig. How much is the Zig toolchain dependent on the Zig language, in the sense of how much is the language part necessary to run the full toolchain and compiler and whatever?
Yeah, great question. So if you're just using Zig CC, 0. If you're using the Zig build system, a Zig build script is written in Zig, so you will have to write Zig. This is like a bit of a nitpick, like a small nuance thing, but Zig also has its own compiler RT, and that one is written in Zig. So probably like if you're targeting a CPU that doesn't have hardware, I don't know, floating point instructions, and so you have to provide like a software implementation, you will get a Zig implementation. It doesn't matter to you, like you're never going to see that code practically, but that is also the last bit of Zig stuff that bleeds into the toolchain aspect of it.
Any more questions? That's it then. Thank you very much.
Thank you.
Yep.
Prova. Okay. Piccolo. Guarda. Okay.
Okay, thank you everyone for coming. Just a reminder to ask questions on the Slido. You can find the link on the website. I'm happy to announce our speaker today, Davide Brunato. He's a DevOps engineer at SISSA in Trieste in Italy. And he's going to talk about how abstract-based classes can help you to solve difficult challenges. The stage is yours.
Thank you. Welcome to everybody. I start the talk about abstract-based classes. This is the agenda. I tell about me, a small recap about base classes, XPath and the library that support that I develop. Then the tricks that I adopted for resolve difficult challenges in my libraries, about regex translator, and then the implementation of XML schema data types, and then the conclusions. About me, I'm a system administrator and then a developer, Python developer, at CISA, that is an international school that provide PhD courses in for mathematics, neuroscience, and physics. We have about 280 PhD students, also a master for communication of science. Our research institution has been founded in 1978, and the research lines are on astroparticle, many cognitive neuroscience, many of them in the areas that I tell. A small recap about base classes has been proposed in 2017. The proposal is for have a way to overload instance and subclasses. A new module that supports a framework for defining meta-classes and ABC, and a decorator for defining abstract modules in more strict way. There are many ABCs for containers and the iterators in a collections.abc module. How to define an abstract-based classes for who that never see that. You can import the ABC-based classes and then derive your own ABC. Otherwise, you can you can define your ABC with using the meta class ABC meta. The type of an ABC is not the basic type for objects, and is ABC meta for whom that never have seen meta classes, worked with meta classes. Be careful of meta classes conflicts. If you have to use them, you have to provide. You have to put careful in defining your own meta class. So better to derive from ABC meta your own particular meta class if you have to do that. Characteristics important of meta classes, ABC meta classes, are virtual subclass. So you can override the standard class hierarchy, and using a subclass hook, that is a dunder method that you can define in your meta class. Another way is to register you can register, show here. If you have a meta class, derived for abstract meta class, sorry. You can register, in this example, a tuple as a subclass for of your ABC, and also is instance an instance of tuple is also an instance of your defined abstract meta class, abstract base class. Okay, abstract methods force you to define a set of methods that you have defined as abstracts before instantiate classes, objects of these classes, of this class. Last, about collection.abc is a collection of abstract-based classes for containers, and you can use you can have three many options for using ABCs, deriving directly from one of the classes provided by the collection, or you define a class that define all the methods of the ABC and use the virtual subclass registration and test the compatibility with this instance and this subclass. Or define a class in a more simple way that has at least the methods required to pass this instance and is a subclass checks against the ABC. For my case, I use a direct derivation, and the best fitting cases I have a structured I have to develop XPath and support XPath parsing, and I use these classes for deriving my types and provide a dynamic programming generation of tokens. In these cases, I think that abstract-based classes are particularly useful because, as you can see, there are some abstract methods, and those methods these methods are the only methods that you have to implement. The other methods, mixing methods, you don't need to do that. So there is less code to implement. As in this case, an example of a minimal implementation of a mutable sequence that is a list. In this case, implementing only this code, you have a full working replacement of a custom list that is also compatible in all the way with other methods. In this case, the list is also a mutable sequence. So you can use mutable sequence as a base class for type checking instead of lists. Now I go to the implementation about XPath and the element path library. A timeline for this activity. I started coding on Python for this, implementing validation decoding the XML data for Quantum Espresso suite, that is a Fortran suite for quantum simulation that is widely used in the community. They need Python as for testing and for validation of XML data produced by the codes. In 2016, I published the first library that is XML schema, and in 2018 I derived a specific dependent base package for element path. Both libraries are now in the catalog of Italian software as required by laws. XPath and XML languages. On the left, there is the historical vision about the development of these languages. On the right, after XPath 2.0 and the next implementation, the graph is on the right, where Xlink has been replaced by XML schema. XPath is still the core of the processing of these languages. The first challenge was about implementing the processing of XML regular expressions. In XML, there are some tokens, some definitions, extensions of regular expressions for matching name and Unicode XML name patterns. As you can see, in XML schema, there are many in the base definition, in the meta schema of XML schema. There are also base definitions of these patterns, particularly the shorthand \C and \EI are new and only in XML regular expression definition. These expressions are used also in XPath 2.0 and XQuery 1.0 functions, in these functions. So after initial develop, appeared clear to me that there is no way without to support a validator for XML schema and then for XPath without implementing a solution for that. Some challenges on that are simple and are defined in the definition of XML schema regular expression. You can replace the shorthand \I with a string, with a set of a character set, a class with this string, and also for the shorthand \C. The other challenges are more complicated, and particularly the last, that the standard for regular expression in XML require the parsing of character class abstractions. That can be complicated because it can be nested. Also, there are negated form of previous character class, and so the problem is that operations are on all the Unicode character set, so the subset of character set that you have to process can be very wide. At last, the implementation support in the element path.regex subpackage. The translation process is about the regex is parsed for tokens that are not defined in the Python regex engine. Parsed token tokens are replaced with the appropriate subset of Unicode characters. The resulting expression is then compiled and used in XML schema processing. There is the import that are relevant for implementation. The problem of Unicode characters, there are currently about 150,000 characters defined, assigned. Each assigned character has a unique identifier name and is mapped to a unique immutable code point. Python 3.8 supports the Unicode character database 12.1. The 3.12 is compiled with Unicode version 15. Code points. There are more than 1 million code points. Most of them are not assigned yet, but is increasing version by version. At each code point is assigned a general category, and this is the main challenge to resolve. You can support the processing of XML regular expression, processing this subset. Or in other implementation, I saw that they have used a tricks similar, because processing all the Unicode categories row with the subset involve the problems of memory. Also about memory usage of dictionaries for storing these categories. At least you have to use about 10, 12 megabytes for a subset for all the categories. You have also to process them, and this is a problem. To resolve that, about abstract base classes, particularly useful has been for me to implement a mutable set, that abstract base class from abstract base class, processing not the whole set, but only a subset of intervals, because the characteristics that permit to do that is the fact that code points are grouped in about 6,000 intervals, so it's processable, and most of them are in undefined set. So using a list, a ordered list, I can process as a set with a full API of a set the operations that I need to do to process XML regular expressions. Profiling this Unicode subset as for verify if it's usable in terms of time, in terms of memory, the memory impact is very low, and the time is acceptable. With the Unicode subset, I can also process intermediate operations and create the list is longer, but use a Unicode subset to create at import time all the subset that I need to process the regex to process the results. I compile the regex. The translator is a function that returns a Python regex that can be long, but is compiled by Python and then used in XML schema. So in the case that I just illustrated, the abstract base class of mutable set has been useful for providing less code and to be sure that the subset that is produced is full operational with the setup API in terms of characters or in terms of code points. The second challenge is about atomic types and the expat data model. On the right, there are the XSD 1.1 hierarchy of types. There are some problems about that because any atomic type is the root type of any atomic types in XSD, but it's not instantiable. Also, I have to support in XPath untyped atomic and numeric that are not. Untyped atomic is another type that is not in XML schema, and the numeric is only for checking numeric data. So the solution, other challenges, is about that double and float are different types in XML schema. Is Boolean is not an integer. Also, integer is a subtype of decimal. And requirement is about the will of using basic data types whenever possible, because at that point that I did this implementation, the libraries are already used by many programs. Where are XML schema XPath types used in XPath? Are used in some their instructions of the language, or for specific conversion casting of type, instance checks, or to check if a type is usable as another. The implementation uses abstract-based classes using the ABC meta, in this case, to override the instance check of that is the main, the specific characteristic of abstract-based classes, and this was very useful to implement this. Otherwise, I cannot imagine how I could do that, because the instance check is explicit in XPath, and so I have to reproduce this case in my code. I derived a meta class for doing that, and then the atomic type. The implementation of float has been with another, I derived directly from an atomic type in this case, in some cases, and float has a pair of classes for processing the creation and the validation of the data. The meta class provides also a return back a validation is valid, invalid type, and some other things to, okay. Now to the other implementation. I describe only this. About I defined some proxy classes derived from any atomic type because I don't want to replace the basic data types, but I need the checks of under the type system that I've defined. So XS Boolean is validated. The creation of instance is done by a Boolean proxy that returns a Python Boolean. The subclass hook permits to check the instance. Solution for string types is a bit complicated because I wanted to use a basic Python data type. So I derived the normalized string that is the the direct derivation from string, the first derivation from string, both from string and atomic type, any atomic type. In this case, I provided validation, and well, it's a bit complicated to describe here, but also in this case, a proxy type permits to validate that. Solution for integer, similar to this. Also, I used the subclass hook to check the types and that it is not a Boolean. Conclusion about that: if you have to implement a complicated hierarchy of custom types, abstract base classes can give you flexibility to override, and it is the only way to do that that I found. Other checks on types is very, very complicated on values, and so make the code, the program slower, and reduce the code provided from necessary to implement your solution. This is the total. These are the totals for the subpackages. regex subpackages has about 2,000 lines of code that are 2 or 3 less than the other implementation that I saw in that are Java in these cases. Data types, implementation is full, supported, okay, is finished, and I finished, and particularly important, the implementation is full about also the date time types that are an extended version of date time of Python with checking of time zone and with dates before the common era that are full supported. I pass with this package. Thank you for your attention. Now the package support about there are about 50,000 tests of XPath 2 and then more for XPath 3 and 3.1. Okay, thank you for your attention. Sorry for the English. For my if there is one question. Okay.
Thank you very much. So we maybe have time for one question if you have it live.
Okay.
We have no questions online. Thank you.
Era meglio non farlo.
Prova. Okay, everybody. So then our next speaker is Roman. He's a platform engineer working at Auki Tech. And he's going to talk about Python-friendly cloud infrastructure management. So give an applause, please.
Hello and thank you. Yeah, it's working. My name is Roman Prokhotchenko, and I'm pretty glad to see so many people who are developers and not afraid of the infrastructure here today. Well, probably that has to do something with the wine that give on the restaurant, but we'll try to get the way around the infrastructure management that does not require consumption of any kind of wines or alcohols. So as I said, my name is Roman Prokhotchenko. I am a cloud engineering consultant at Auki Tech, and today I'm going to talk to you about Python-friendly infrastructure management. And by friendly, I mean that it should be friendly for developers, and you'll see why. So I spent over a decade working as a Python developer myself, working mostly in the field of automation and infrastructure management. And I've been hearing this statement a lot, that developers avoid infrastructure. I had been biased all the time. I've been working with the infrastructure. I loved every aspect of it. I liked the idea how you can write a software, even tiny piece of software that can manage the entire and expensive data centers. But then later I switched to site reliability and platform engineering, and then I started teaching developers how to build reliable systems, and I realized that it's actually true. And when you start talking to developers, they love coding, they love creating software, but as soon as the work starts talking around infrastructure management, it can get tricky. Developers try to delegate these jobs to someone else. They try to escape from it, in short. And I've been given that a thought about why this happens. What is the nature of this avoidance? And my biggest theory is that it's complexity. Because through the recent years, infrastructure became immensely complex and immensely complicated. And if you give it a thought and you take a look back at the infrastructure maybe even 10 years ago, that you will see that it was simple. It was very familiar with the developer's environment, and then you developers could run, you write your own software on your personal computer or laptop if you were rich back then. Then you run, you test it, you see it works locally, right? It works on your machine. Then you just copy it to the server. Maybe there are a couple of them if your organization is rich again. And then you run it there. Then it's accessible to users, and you would understand where it runs, and how the users access it. So the most important part of it is that you as a developer would understand how to test that it runs properly on that production environment. We faced several changes in business requirements to the production infrastructure, and now it looks a lot different. Now it has many loosely coupled components. There is a lot of ephemeral stuff going on there. There are containers, serverless computers, whatever. There are different ways to do the infrastructure, but none of them looks like your typical development environment. So you as the developer now write your application, write your code, you test it locally, and then in order to put that to production, to get real workloads from users, you would need to do use some sophisticated tools which are no longer in your developer ecosystem that you normally use. And then when the application is running there, you often don't know exactly how it is running, because it's not your developer laptop. It's a Kubernetes cluster with serverless components there, right? And you don't know how to test if it's running properly there. So to tackle this situation, operations people or DevOps people, you call them, there's no single conventional name in these people, they gave you a range of tools which are called infrastructure as code. And well, we sort of decided that this will solve the situation. This will solve the problem, and developers will love working with these tools because code is code, right? Like meat is meat. Doesn't matter if it's pork or beef. So like code is code. So every developer will like working with it. And then it didn't necessarily happen. So it helped a little. It helped to tackle the situation a little. But then we faced another situation, another problem of infrastructure as code approach is the isolation of developers. We somehow assumed that developers will love working with our tools that we gave them. And we didn't realize that developers work with the stack of technology they use because they love it. It's not because they are, being forced by someone to work with Python or with Java or with any kind of language. And you love working with the technology tree that you've chosen. You know the ecosystem, you know the tools, you know the editors, you know IDEs, everything. So you have your habits, good and bad sometimes, in working with within a certain ecosystem, and you don't necessarily want to change it. And if you take a look at the infrastructure as code, mostly that looks like an alien language because that's normally, it was never Python, it was never some Kotlin or other fancy programming languages. It was some other programming language that you would have to learn, like Puppet. Well, it's based on Ruby technically, but doesn't matter. So you would have to learn it, you would have to onboard onto the ecosystem because it's not the language on its own. It's the whole ecosystem that would have to learn. And if some of you work in bigger corporations where you have development teams, smaller development teams for smaller scope projects, then you may have seen the situation when one or more developers would be designated being a developer, the infrastructure champion or infrastructure liaison, you name it. But basically that would be a person who is designated to be onboarded into the infrastructure as code tools and do the infrastructure for the whole team. But in the talk description, I promised you to show the way how to do it not only in bigger corporation that has the capacity in the teams to designate people to do the infrastructure for them, but also in smaller setups. And why is this important? It is important because none of us is working here to write the code. Well, maybe someone is working here to write the code and getting paid for writing the code. Show me your company, I'll join. So we're not working there to write the code and that's it. We work here is to build systems. As infrastructure people, as developers, as DBAs, we work to build systems that solve business purposes and serve our customers. And there is one fundamental law of systems engineering which works wonders, and it works every time. And that law was formulated by Melvin Conway a while ago. And it states that organizations are restricted to build the systems which reflect the communication structure inside of those organizations. So what does it mean? What does it mean for us, for operations, for developers, for DevOps? That means that if we disconnect software and infrastructure, if we disconnect developers and operations, that means we will write software that is not solving business purposes effectively on the existing infrastructure, or that the infrastructure is not ready to accept the software that it is running. And this will cause tons of different issues. It could be not cost-effective system, it could be not performance-efficient system. You will have issues with upgrades. Like, there are dozens of issues that will happen if the software and the infrastructure is disconnected. And this is why when I speak to the companies, I always tell them that developers shouldn't avoid the infrastructure. And that does not mean that developers should do the infrastructure and take the responsibility for it. No, it doesn't mean they have to, but they shouldn't avoid. They should be kept in the communication circuit with the ops people and with the DevOps people, you name them, how it could be called different companies. And software and infrastructure should be built for each other. So software should take into account the architecture, infrastructure architecture it's running on, and vice versa. The infrastructure should be prepared for the software. We need to break the silos for that. To break the silos, it's always required. We always require mutual effort. You cannot break the silo from just one side. We cannot just introduce developers with the infrastructure as code tools and expect that they will use it, because the effort is required from both sides. So we need to understand how to make infrastructure as code approachable by developers and how to make them love these tools and be friendly to developers, to Python developers in this particular case. So let's take a look at the existing tools that are in the market and let's try to choose one, preferably one that is going to be easy to use and that will solve the situation for us, that will be friendly to developers. And every bigger cloud provider, public cloud provider specifically, they have their own tools. Like there is CloudFormation for Amazon. There is CDM for Google. There are also tools which are agnostic to the vendors like Pulumi or Terraform. You may have heard about some of them, and they allow you to manage the infrastructure in different clouds, even private clouds if you have OpenStack or similar software. And today I'm going to focus on Terraform from HashiCorp. So why Terraform? Terraform is a mature, industry-grade, and widely adopted software, which is used across the industry by smaller and bigger companies there. And this shows up in the friend list later. I will show you. So your typical Terraform setup for infrastructure management consists of several key components. There are manifests. Manifests is where you describe how you would like to see your infrastructure. And then there is a state file. State file describes what actual infrastructure you have, so how you want to see it and what you actually have. And then there are infrastructure providers that are designed to work with the different infrastructure providers. So then the task of Terraform is to compare the manifests and the state file and combine a set of and create a set of action called plan to make the infrastructure from what it is to what you would like it to look like. And for developers, the infrastructure management workflow is simple. You change the manifest, so you make the changes into how you want to see your infrastructure. You create the plan, and then you apply the plan. And ideally, you have your plan, your infrastructure, in the way that you would like it to be. It doesn't happen every time, of course, but most of the time it happens. So manifests themselves, they are created with the declarative approach. So again, you state what you want to see, not how to do it. Terraform decides how to do it. And normally you create them with the Terraform's domain-specific language called HCL, which stands for HashiCorp Configuration Language. And the simplest example I could come up with looks like that. So if any of you is familiar with Amazon, in this example, we create a messaging queue in Amazon SQS service. We give it a couple of parameters. And in theory, this should give us a messaging queue on Amazon. And like this presentation is not a real life scenario, right? I'm not going to lie to you that and say that it's always that simple. So this is a little piece of infrastructure from a relatively small project that I've seen recently working with one company. And it gets complicated. It gets complicated, especially when you need to create the configuration based on some conditions. And again, HCL is not Python. I've been saying that we should make it friendly to Python developers, which are familiar with Python infrastructure, with Python ecosystem. And this is not Python, it's HCL. So normally with bigger companies, I always tell, designate a person who will onboard to Terraform, because HCL is the best way to define Terraform infrastructure. There are multiple reasons for that. I'm not going to deep dive into them. But again, we're talking here about how to make it friendly for Python developers. The beauty of engineering process is that we're not talking in absolutes. An engineering process accepts compromises to build better and reliable systems. And so while HCL is the best way to define Terraform manifests, Terraform also allows developers to do infrastructure definitions in other languages with the Cloud Development Kit that it offers. Cloud Development Kit usually shortened to CDK, and it shows in the tools that I'm going to show to you later. So luckily for us, Cloud Development Kit from Terraform supports Python language. Just give me a second. And you would need to write some boilerplate project in order to start creating infrastructure, but luckily you can generate that boilerplate with the CDK-TF, which is a tool that you normally run on your computer, install and run on your computer. You get a template of the project like that. So that looks already closer to Python people, because it's Python. It's a Python class, it's some Python imports, and you may even see that one of the files is called tests. The reason for that is because you can test Terraform infrastructure using CDK and PyTest. So it's normal Python unit tests that allow you to test the infrastructure. Let's get back to the previous example. So this is the SQS queue that we created before. How would it look like in Python? Like, behold, it's that. So given some boilerplate that you have seen before, it was generated. We had to create an instance of the cloud provider to initialize it, the client, and then we just had to declare an SQS queue with the same parameters. You do it in a Pythonic way. Now you can use your favorite Python IDE and whatsoever. Then you can immediately see how you can use Python language features like list of strings to generate several queues, and you don't have to think about how to do it in HCL, how to do it in the Alien technology. So once we're happy with the manifest, we can run cdktf plan to create the set of actions required to create the infrastructure. In this case, we had no queues, so Terraform is trying to tell us that it's going to create 2 queues. I trimmed some output because it's a little bit wordy. Once we're happy with the plan, we run cdktf apply. You can see it takes a little bit of time to create these queues because it requires communication with real cloud provider, but then later when it's finished, you have the queues in your Amazon SQS web console. And if you deep dive into that, you can see that here we set up the tags that we have been setting up in the code. But then you ask me, Roman, but again, this is all great. How do I know how all these different classes are called? What parameters they accept? And this is the beauty of Terraform's maturity. It's mature, it's widely adopted, so it comes with extensive and very well-structured documentation. This is called Terraform Registry. It has all the providers. It has beautiful search there. You can just go and enter the name of the resource you want to create. You switch the language examples to Python, and you get all the Python examples for you. You also get argument reference and attribute reference, which help you to tell what attribute to set. But frankly, I never use this search. The wide adoption of Terraform causes that if you enter Terraform and then the name of the resource you want to create into the search, you will get it. You will get it fast. Well, you see. Does it take the complexity away? I reckon it doesn't. It allows you to create resources in Python. But then if you take a look at a simple platform to run applications on, Kubernetes is a popular one, you would have to create 40 configuration changes just to create one small production-grade Kubernetes cluster on Amazon. For you as a developer who writes manifests in CDK, that would mean you would have to create at least 40 IAC definitions. And we haven't started deploying yet, so we just create the platform. And how would you know what is the best combination and the default values for a production-grade platform? You would have to onboard onto the infrastructure management completely. You don't have to. With Terraform, you have modules. Modules are pieces of infrastructure definitions combined together, which will have same defaults and have opinionated structure for bigger chunks of infrastructure like EKS clusters, database clusters, even SQS queues. They have some patterns of being used in a good way in production. So modules provide you the way to do it right from the first attempt and not dig up into specifying 1,000 of correct parameters. So modules usually look like that. You can also find them on Terraform Registry. There's extensive documentation with examples there. And every major public cloud provider has a namespace in Terraform Registry. There's Terraform AWS modules for Amazon. There's Terraform Google modules for GCP, and for Microsoft, there's Azure. And Microsoft, you know, likes naming things differently. So here we go. So how do we use these modules? Like, how do we create an EKS cluster? First, we'd have to define them in our cdktf.json file. Don't worry, I will attach all the examples to the in the end of this presentation, so you will be able to explore it. So we first declare what modules would you use. In this example, we use the EKS module for the EKS cluster, and VPC, that's basic networking layer in Amazon Web Services. And later, I trimmed down some of the boilerplate code, but that's the same sort of resource definition. Instead of defining individual resources, we just define these modules. So you can see there is some code here, right? But if you think about it, we create a networking layer, a production-grade networking layer, and the whole EKS cluster is going to be scalable EKS cluster with this much of the code. So for me, that's a big trade-off. It's like maybe 30 lines of code here for a production-grade, small production-grade cluster, which will be scalable in the future, and you will not have to migrate all the workloads somewhere else. Applying this takes around 35 minutes, but then it pays off with a cluster. So you have a cluster, you have node group there, you have base layer configured, and of course, you can start using it just like that. If you want to play around with the examples, you can simply scan this QR code. It will be available in the end of the presentation. You can follow by the repository. All the examples are there. They have been checked to work. And there are much more examples available on the Terraform website. I will provide all the links later. So we solved the issue of creating smaller components in Python. We solved the issue of creating bigger components in Python. But then when you start working on some product and you need to build the whole infrastructure from scratch, you might question yourself, what kind of architecture of my infrastructure should I choose? And then you start deep diving into public clouds. And you may end up in a situation that you will think that I probably need my PhD degree to get into one of those public clouds to understand what they mean by those. So do I need EKS, ECS, GKE, Fargate, or WNMATI? The letter stands for whatever new marketing abbreviation they invent. So what do I have to choose as a developer? I hope I didn't press anything bad here because I pressed something. What solutions, what basic architecture for my infrastructure should I use? And bigger cloud providers like Amazon, Google, and Azure, they saw this problem. They saw that developers cannot create their infrastructure easily from scratch. And they ended up with reference architecture documentations that they publish, that they update regularly so it matches the current business requirement. And you may find them in Amazon or Google Cloud or Azure architecture centers, which are available by these links. You will get them later. What you need to do is to open the architecture center, search and filter your particular use case, and you will find, just a second, and you will find, most likely you'll find an example of good architecture, which is well thought, which is battle tested for your particular application. So whenever you're working on a Django e-commerce app or you're working on some messaging app, you'll find something there. So here I have a screenshot from a document for Python applications with hexagonal architecture, for Python infrastructure with hexagonal architecture, and it's very well structured. It has tons of examples, and it's ready to use for you. You can just use it. So we tackled the situation of having to write manifests in your favorite technology. We overviewed how we can create bigger chunks of infrastructure like EKS clusters, RDS clusters, and even SQSQs that sometimes need to be configured accordingly to be production grade. And also, there's a reference to the architecture. So with that, I hope you will be happy to onboard onto the infrastructure adventure with the rest of the developers. Thank you. If you have any questions, I will be happy to answer them. So that QR code provides the link to the same repository with the same examples. There is a bunch of links there, so everything I mentioned has a link. So you can go ahead and save it for yourself.
Thank you, Roman. So we have a couple of questions on Slido. The first one is, why developers have to learn about infrastructure things and write EAC, but operation learn so little about programming?
So the idea is to not have operations at the company per se, but to have a platform engineering team, which gives developers the way to build the application infrastructure within the development process. Again, if we have developers not thinking about infra and operations not thinking about development at all, we'll have a disconnected situation there where infrastructure will not be ready to host the app and vice versa. I've seen a lot of situations when developers write a lot of extra code instead of using better deployment scenario. And then supporting that code is expensive, writing the code is expensive, and then the code is bug prone. If you use it's often possible to solve business requirements without writing the code, but with just using proper deployment. And the other way around, if the ops team is responsible for building infrastructure and the ops team doesn't want to learn programming, well, we will not have infrastructure that runs products effectively. So I'm not saying operations shouldn't learn about the infrastructure. I am saying here that operations should transform into platform engineering team that will be building tools for developers, so developers can easily and conveniently manage the whole life cycle of their applications without the necessity of creating tickets or learning deeply about how the infrastructure works. Developers have to have a convenient way to do the things right from the first attempt. That's it.
Okay, thanks. So the next question is, how mature is a CDKTF really? I heard mixed feedback from users about many bugs and bad documentation. Would you recommend to run it in prod?
I tried CDKTF in prod. It works for smaller teams. If you're a bigger team, HCL is the way to go. That's a simple answer. If you don't want and you don't have the capacity to onboard into the HCL, well, you will not use it. You will start creating the infrastructure manually. So on the scales, we have on one side manually managed Frankenstein monster of the infrastructure, which would have to be migrated completely soon. It happens all the time. And on the other scale, we have a not so optimal infrastructure as code that works. So I would choose the infrastructure as code that works, that is ready to scale later. It is possible to migrate from CDKTF when the company or the team grows, but it's very hard to migrate from the manually managed infrastructure when nobody actually remembers what there is to any kind of infrastructure management tool.
Okay, thanks. So next one, how do you deal with the Terraform license change? Is there something comparable to CDKTF in OpenTofu?
Pulumi is a good way to go. However, it's not that widely adopted, and I would say many developers use Pulumi. I don't use that in production. I tried it out. It actually works. It allows you to do more crazy things with the infrastructure as code because it's more software oriented, and I reckon developers should not get too creative in the infrastructure code because infrastructure code should be as simple as possible. So probably using meta classes in infrastructure management is not a good tool, is not a good idea. But yeah, like Pulumi is a good way to go. And if Terraform is not compatible with the way the company works, license-wise, yeah, Pulumi is a good way to go. It's better than manual infrastructure management.
Okay, so another question. What do you advise for testing the infrastructure? Running PyTest integration tests to test your Kubernetes cluster in the CI stage and wait 35 minutes seems not ideal.
So not all the infrastructure changes require 35 minutes, and you most likely deploy Kubernetes cluster once in a very rare while. Usually, I vouch for putting tests for the infrastructure in the same pipeline of the application deployment. So every commit, if of course that's the scenario you can afford, because if you have a service that's publicly available to users, that's the scenario you can afford. If you have a product that is being shipped as part of distributions, that process is not for you. But if you have a service that runs constantly and users have access to it, then you can even result into one single pipeline that has all the tests for the application, for the container security tests, then the infrastructure tests, and then we have deployment to staging, end-to-end tests, and deployment to production. I've seen these scenarios. So that works. And this is the way I would like to encourage developers to strive towards. It increments the ability of the company to react to incidents or business requirements faster, and it improves a lot of other business metrics.
Okay, so another question. Can you automatically audit the Terraform code for insecure configuration?
Yes, Chekhov is a good tool to use, for instance. Chekhov. I don't have anywhere to write, but please catch me up later. I will to show it to you. It has a lot of patterns already there to detect if you don't create some fancy configuration, which bad people would fancy to see in your production environment. But you may also run the custom checks there. custom tests. You can create your custom policies for a company. For instance, you want to say that every database cluster should be protected from deletion and have the encryption by default. If not, well, we don't pass to the stage when we create the actual infrastructure. But then that's one thing. Like, you have to also protect the infrastructure from the other, from accidental changes made by some other people. And I would recommend to use live infrastructure monitoring. Constant tools like Cloud Custodian are good for that. So you just run it. You have another set of policies that check the infrastructure how it is. They don't check so you should not only check the manifest. You also should check the production infrastructure there.
Okay, thanks, Roman.
If you have further questions, feel free to catch me up or drop me an email or submit the contact form. I'm usually prompt to respond. Thank you.
Okay, everyone. So our next speaker is Christy. Christy, an AWS serverless hero and a principal software engineer at Liberty Mutual Insurance. And she will talk about snake and ladders, the ups and downs of Python development with AWS Lambda.
All right, so 3 days of Python content, and you are all still here. So this means I have the super fans in the room. Thank you for the introduction. Yes, my name is Christy Peralt. I will be talking today about Python development with AWS Lambda. But before we get into that, did some exploring around Florence and this beautiful city. And I don't want to make anybody jealous, but I was lucky enough to see the snake while I was here. So maybe you can get a chance if you check it out. On a more serious note, I am a very structured person, so I put together a quick agenda for us today, though I don't want to constrict too much. Cheesy Python jokes. So a quick introduction of who I am and how I kind of got to be here. We'll talk a little bit about what AWS Lambda and serverless technology actually is and what that means. As with anything, there are definitely challenges with this, so we will cover challenges in Python development with the cloud. Some more snake puns for you, but we'll talk a little bit about solutions and some support that we have in this space specific to Python. And then everybody's favorite topic is testing, so we will cover testing as well and how that can help us out here. And at the end, we will recap and have some time for questions. So a little bit about me. My name is Christy Peralt. I am a principal software engineer at Liberty Mutual Insurance. I have been there for about 8 years, but the last 6 have been focused purely on cloud and serverless technologies and engineering. So I worked in our DevOps engineering space and have kind of transitioned into cloud education as well as engineering enablement and building developer tooling, a lot of which has been in Python. I am very involved and active in the AWS community, so I've done a ton of speaking events and podcasts, attend a lot of conferences, speak at a lot of conferences, and about 2 years ago I was recognized as an AWS serverless hero. My fun pandemic activity was getting a master's degree in electrical and computer engineering, so I do like to share that because all of my cloud knowledge and serverless experience has actually come straight from real-world industry experience, on-the-job training and learning. My background in education is actually way more on the hardware, robotics, hands-on circuitry end. So everything that I'm talking to you about today, I have learned in my job. I am from New Hampshire in the United States, so a little far from here. I organize the Portsmouth user group with a few folks, though I do spend a lot of time on this side of the pond, so I'm also a co-organizer of the Belfast Northern Ireland group as well. And I'm a huge advocate for women in tech, so I work a lot with young girls, inspiring them to pursue educations in STEM. I was very active in the local Women Who Code community up until recently, when they've unfortunately closed their doors, so I'm hoping that we can get some more women in tech organizations started up in their place soon. So that's enough about me. I wanted to set the stage a little bit here. Quick show of hands for folks in the room. And don't worry, I won't call on anybody. I don't like putting people on the spot. Who is familiar with AWS Lambda and serverless? Okay, so a lot of you. I don't know why you're here then, because this is supposed to learn about it. So I want to just kind of clarify what that means or what that is for folks that maybe aren't as familiar or haven't had a ton of hands-on experience with this. Since this is a Python conference, I do want to cover that Python Lambda is not the same as AWS Lambda, though they are similar in kind of meaning and definition. So they both are small functions that are used to do something. So a logical component, something that you can build. Usually a Python Lambda is much smaller. It can take a number of arguments, but it's typically only one expression and a couple of lines of code. AWS Lambda is a full-blown compute service offering from Amazon. So it is small, but small is relative here. It just means a smaller script, smaller compute, but it's definitely more than just a couple of lines. This is deployed to AWS as well, and they interact with a bunch of different services. So typically, if you're using an AWS Lambda, it's maybe triggered by something, whether it's clicking a button on a website and doing an API gateway call, or with storage, Dynamo, and other RDS options as well. So typically, a Lambda function will be triggered that way and can interact with other services. So you may use it to do a GET or a POST call and interact with a database, or a blob storage or something similar. This is not Python specific. You can use any language or most languages for AWS Lambda. Python is the second most popular one though. So there are a lot of Python developers out there using the cloud and using AWS Lambda. TypeScript is number one if you were curious, but we're getting there. We're almost caught up to them. So why might you want to use AWS Lambda? And as I started writing this slide, I realized that everything I put up here was also talking about serverless. So if you're not familiar, a serverless does not mean that you are without servers. It just means that someone else, like Amazon, Google, whichever cloud provider you choose, are managing those servers for you. So you don't need to worry about the underlying infrastructure. You don't need to worry about maintaining, patching, doing some of those things. You really just need to worry about your code and your business logic code. So AWS and Lambda and serverless are not the same thing, but we do use AWS Lambda quite a bit when we talk about serverless. So serverless is more of the larger philosophy, how you're building your applications and the architecture. AWS Lambda is a core compute service for serverless. So usually when you're talking about serverless, it's very common to be using AWS Lambda or the equivalent in other clouds, usually like Azure Functions is another big one. So they're both very scalable. You only pay for what you're using when they're running, which makes it a really easy sell for the business and for your wallet as well. They scale up and down as you need them, so they handle the spikes in traffic that you may have. There's a lot of us that might have some more predictable workloads and kind of know so that this can handle it for you. Quick and easy I debated putting up here, because as we'll learn in these slides, and depending on who you are and what you're working on, some people find this very easy to work with, quick to stand up. Some people don't. Usually with things like startups, smaller applications, greenfield applications, this is really easy to get started with and get moving with. Sometimes in larger enterprises or with legacy code that you're migrating into this space, it can get a lot more difficult and complicated with using these services, but we'll talk a little bit about that later. I mentioned a couple times the event flow, event-driven, so usually serverless is very event-driven, so your Lambda function is going to be triggered off of an event, like a button click on a website, and then that'll pass the event along and return something to another part of your process or even directly to your users. And as I mentioned, this is a managed service, so you only have to worry about your business logic code, some basic configuration setup, and AWS or your cloud provider of choice will handle a lot more of the underlying infrastructure for you. A big one here is security too as well. So typically we say that you are responsible for the security of your application. AWS and your other cloud providers are responsible for the security of the cloud. So you don't have to worry about securing the data centers or the actual hardware. You just have to worry about managing access to your application with policies and roles and some of those other things. So now that we've had 2 slides talking about serverless and Lambda, it is time for your first assignment. And it is a Saturday, it is the end of the conference, so don't worry, you guys don't have to do anything. I will do all of the hard work here. But let's say that your boss, your tech lead, whoever it is, comes to you with a list of requirements, and they're pretty granular, so you know that an event's coming in, probably off of an API gateway call, maybe a post. And you want to do some really light data manipulation on that. So again, this is Lambda functions, so relatively small. We're not talking data lakes and really large data sets here, but small things that you might want to adjust or tweak or update. And then you're going to upload this to an S3 bucket, which is AWS's offering for blob storage. So that would be kind of like a file system. You can put anything up in there. And for this case, we'll talk about maybe JSON files. And then you'll want to deliver a return status to the application or the user. Now, most of us are Python developers, engineers, architects, so we translate this into our technical requirements. So we're sitting here looking at this and thinking, well, definitely going to want some logging and observability in here to see what places of my code are running, where I might be getting into errors, and kind of just overall looking at metrics and things that are happening in my application. You'll want to handle those errors as they come through. And even though this is pretty light data manipulation, Python has really awesome libraries available to us. So we may have a lot of imports, libraries, things that we want to take advantage of and bring into our Lambda function. And finally, with any good application, we want to have really robust testing. So infrastructure tests come along with working with AWS in the cloud, as well as unit test, integration tests, whatever else you may want to use to test your applications. So you say to your boss, that sounds great. I got a 5-minute overview of this from Christy, and it is brand new and greenfield, so I know exactly what I'm doing. This will be quick and easy, as she said, right? Not necessarily the case. So you start developing and you kind of realize that you're running into all of these challenges and these issues with using Python. So just because you went to the cloud and it's the latest and greatest thing doesn't mean it solved all of your problems for you. So you start seeing things like managing dependency conflicts, running into package sizing issues. The biggest one I've seen a lot lately is local versus your deployed environment. It's really hard to emulate those AWS services locally, and it's really hard to recreate that deployed environment so that you can test adequately. Lambda is built on Linux, so anything involving working with the file systems and OS libraries can be a huge headache. I've experienced that firsthand with building developer tools for different platforms. That can be really difficult. And then we're injecting environment variables. You start talking about things like API keys and secrets and the regions that you're deploying to, and this can get very complicated pretty quickly. The good news is there are a lot of very Python-specific tools and technologies that are out there that can help us out with that. So we have some solutions that we can use at our disposal. The first one of these is one of my favorites. It's called Lambda Power Tools. If you know me or work on my team, I push this library constantly to the point where people think I am getting commission for it. So if you do end up using it, make sure you let Ada or Lessa know on the AWS team so that I can get my check cut of this, because I have definitely promoted this a lot. So from their documentation, they straight define Lambda Power Tools as a developer toolkit that implements serverless best practices and increases developer velocity. My second statement here is kind of my own twist on that and what my experience of that has been in more layman's terms. So it's like a wrapper library that helps you simplify your application observability using things like annotations and really straightforward commands. So out of the box, they offer a lot of great features. These are their core ones. So there's a tracer, if you're familiar with things like OpenTelemetry and AWS X-Ray. This is like a wrapper for that. So you're able to incorporate those in your Lambda functions without too much headache and standing up some of these instances. A logger, hopefully that's self-explanatory, but if anybody in here has used AWS, you know that the logs are not always the best. They're not very explicit. This helps you with some more visibility into your applications and your Lambda functions. They have some really cool features with metrics, so they're able to actually send metrics directly to a CloudWatch dashboard for you in just 1 or 2 commands, as well as even forwarding those along to Datadog. And the last one is the event handler, which is probably the one I've had the least experience with, but it works really well with your API integrations, routing, and endpoints. And the thing that's really cool about Lambda Power Tools for PyCon is that it was developed with Python developers in mind. So this is a Python-first library. They've just recently started expanding into other languages like TypeScript. But the advantage here is that we'll get the first features. They're tested with us, and they have the most released so far for Python developers here. So So I was hoping I was going to be a little bit closer to the screen to point some of this out. So hopefully you can see this okay. I am definitely not a live coder, so I pulled some code samples from the Power Tools documentation just so that you can see how easy this is to work with. So the top left is our logger. You'll see on line 1, we import the logger. On line 4, we instantiate it. And then in log 7, there's an example of an annotation there. So you're injecting some basic Lambda context to enrich those logs that are coming through for Lambda functions. And then you can see on line 9 and on line 12, you're using the logger as you normally would. So these are logger.info statements, but they also have debug, error, and the different levels that you're used to as well. And you can see on the bottom left here that this is what it looks like now. So it's added those pieces in blue for you. So you get more descriptive messages, as well as more information about your function, like the name, the memory size that you're using, the ARN, and the request ID. The metrics is the second one I probably use the most out of these. Almost exactly the same as the logger. Your first line, you import the metrics. Your fourth line, you instantiate them. And then this one on the 7th line, we're actually doing an annotation to capture your cold start. So working with Lambda functions because they spin up and down when you need them. There is a little bit of warm-up time if you haven't used it for a bit. So this cold start metric gets captured here and will tell you whether or not that run of your Lambda function involved a cold start time. As I mentioned, you can also create custom metrics. And again, line 10 here, all you do is add one metric. And you can create, this one's a booking example with a unit and the value. So these can be kind of anything you want, and it's super easy to send this to Datadog as well. So this covers a lot of that logging and observability that we need for our assignment. So we continue to code, we continue to work out our Python logic. We go to deploy this, and we realize that you have a lot of imports that we just brought in, right? We kind of predicted that. And AWS has an offering called Lambda Layers, which helps you separate some of these dependencies from your logic. It's a supplementary zip file that zips up all these dependencies for you, and you can share this across different Lambda functions. So if you're using the same dependencies or doing something very similar in another function, you can reuse that. AWS and third-party also offer other layers. So in the example of the Datadog metrics, that's actually offered as a layer. So you can just bring that in, add it to your Lambda function, and you have everything that you need to forward to Datadog. You can have up to 5 layers on a Lambda function, but those cannot exceed 250 megabytes total with your Lambda function logic. So it's very important to know that, because as we're continuing to build this out, we actually realize that our package size is way too big for that. We are not going to fit in that Lambda function. But you don't really want to re-architect your entire application. You still want to take advantage of things like Lambda Power Tools. You don't really want to move away from Lambda. And lucky for us, AWS also provides another tool for that, which is containerization. So if you're kind of in the AWS serverless or containers world, these are kind of two conflicting ideas that can butt heads a little bit. There's a constant rhetoric around serverless versus containers. This kind of melds those two things together quite well. So these are Linux-based container images, and it's basically what it sounds like. You can containerize your Lambda function. You can use AWS-provided regular or OS-based images for custom runtimes. You can also bring your own and create your own, which is great when you work at a large enterprise like mine, and you have all sorts of special requirements you need to use. The caveat to this is that you must use Amazon's ECR service offering, so that is the Elastic Container Registry, so that's where they keep the base images for you. But you can see we can use up to 10 gigabytes of data. So this is way better for working with those larger package sizes, which tend to happen with a lot of these Python libraries. So even though you have a small amount of code, you're bringing in a ton of dependencies, you can still make use of Lambda functions. Now, when might you use one over the other? Because these things are kind of similar. Like I said, the layers are really helpful when they're AWS provided or they're custom ones, so somebody else is managing the dependencies for you. You kind of know what you need. It's there already. It does actually reduce your deployment time by a very small amount, and it's really helpful when you have a lot of smaller libraries that you want to share across functions or across projects. I will say, since you all have stuck with me till the end here, my kind of insight on this is that most of the time, if you're considering a layer, you might want to just jump into containerizing because you are usually hitting that larger library, larger package size. So once you're at the point of kind of considering layers, unless you're using one that's provided or you're going to share them, containers are kind of your easier bet. I've definitely worked on projects where I've started with a layer and just kind of ended up on the other side with containers. It helps you with managing a little bit more dependencies. You definitely have more flexibility. The downside is, obviously, your deployment times are going to be much larger, but if you're not deploying that frequently, it's not that big of a deal. It does, however, improve your cold start time by a small amount as well. So one of the other AWS heroes, AJ, has written 2 really great blog posts kind of comparing and contrasting layers and containerization, and he's done some performance runs on these and has some very interesting results to showcase this cold start time on the containerization. So I will share those and include those at the end for anybody who's interested in checking those out. But they do go much further in depth between the pros and cons between the 2 of these. Now we've kind of talked about developing our function. It's out there, it's in the world, it's working as it should. We may need to update some things. And how are we going to maintain this going forward? How are we going to continue to work with this? And this is everybody's favorite topic, testing. Now, as a Python cloud developer, I'm actually surprised that not more people know about the Python Lambda local package. This is, again, one of my favorites to bring in and work with on projects. It's a quick, lightweight pip install. And it's just a CLI command that allows you to run your Python Lambda functions locally. So it's a great lightweight way to run your Lambda functions without having to emulate a ton of things or stand up a ton of infrastructure. You use and send it a mock input as your event, and then you pass in environment variables and some local configuration if you'd like. And I tried to kind of point it out here, the different components of this in the different colors. So all you have to do is run your Python Lambda local. The yellow is just the path to your function that you're going to run. And then in green here is a path to your test event that you're going to pass through. So I usually create like a test data or test event folder and put a whole bunch of different examples in there of different ways that I might expect events to come in, errors, happy paths, different configurations, and then you can kind of run through all of those. Optionally, in the purple, you can add in environment variables if you need that for your Lambda function to run, and then a quick timeout value, which usually this does not take that long to run. So this is a super powerful library that I really like to use when I'm testing locally. It saves you from having to keep deploying this up and maybe clicking the button in the console and pasting in new events. You have them all right there with your code, and you can package that up with your testing. Now, some of you may have heard of the Modo library. I can't talk about Modo unless I talk about Bodo. So Bodo is the library that you use to interact with your AWS services within your Lambda function. So if we think back to our assignment, one of the things we want to do is upload to an S3 bucket. How do you do that? It's with Bodo. So Bodo, you can stand up a client or a resource. So we'll create a bucket maybe with S3, and then you can simply do an S3 put object, and you put in your key for your file as well as the data for it, and then point it to the bucket you want it to go to, and you have uploaded to your bucket. Modo is Bodo's mock library, so they were very clever with mock Bodo, becomes Modo. It allows you to mock these standard services for your unit tests. It's not meant to replace anything else, but it is really complementary to things like PyTest that already exist. And again, this is something that is very specific to Python development with Lambda. So I have a couple more code examples straight from the documentation again. So the top one is your actual code. As you can see, this is pretty easy, exactly how I described with importing Bodo, you're going to set up a client with S3, and then you're going to do a put object. So that's exactly what we want to do in our assignment today. And then the test is a couple of different lines. There's a couple of different ways you can use Modo to mock in your tests. This is one of the easier ones, so you can see on that fourth line there, you're just bringing in a mock AWS annotation, and then you're creating your resource, and it knows that that'll be your mock that you'll want to use within your tests. As I mentioned, it works really well with PyTest as well. So this one on the right shows some PyTest fixtures that you're going to initialize your tests with. And you can do a with mock AWS and yield the client and create the S3 bucket there as well. So there's a couple of different ways that you can kind of implement this in your tests. These are some of the easier ones, but the documentation covers some really good ways to do this as well. Now the last one that I want to talk about today is actually not AWS Lambda specific, but it is Python specific. It's Tox. It is a virtual environment manager that helps you run your tests. Again, super powerful tool. I do use this in all my AWS projects, and I encourage my teams to use this as well. Kind of like your package JSON just for tests, or bring in your requirements that are just for your tests. You're able to point it to your test paths that you want to look at, as well as set up your own environment variables here. If you don't want to initialize that in a PyTest fixture, you can do that here. And then you can set up your own commands. So I like to use poetry quite a bit. So we have our poetry runs in here. And you can even set up different ones like unit testing, integration testing. You can even set up linters and things in here as well. So you can run Tox unit, Tox integration, run all those things separately, or run them all together just with Tox, TOX. So this is a very low left thing to add to your projects, and I think it makes all the difference and definitely saves a lot of time when you're working with your cloud. So we've implemented all these things in our projects. Congratulations, it was a huge success because we took advantage of all of those great Python libraries and tools that are available to us. Hopefully we have learned something from this, and you can go and enjoy a gelato. First off, I can definitely chill on the snake puns and the snake pictures. I definitely thought he was too cute and went a little too overboard, but we'll relax a little bit on that after this. Just kind of in summary, Lambda is a really powerful cloud compute service, but that doesn't mean that Python issues go away or don't exist anymore. It still can be really difficult to develop with Python in the cloud. We do, however, have really awesome, up-to-date, made-for-language Python tools that can help us out when we're developing in this space. Tests are still definitely important. They are very complicated in the cloud world. We do our best to kind of work with and emulate deployed environments as much as we can. It's not always the most perfect thing, and sometimes you do need to manually test. But we have really cool tools like Python Lambda Local, Tox, and Modo to help us out with mocking these services and hopefully not make them too complicated. And I hope everybody here can sort of walk away with this idea that they can build fully serverless, scalable applications with Python in AWS or any cloud of your choosing. So it's maybe not the quickest and easiest way, but there's definitely a lot of guidance, a lot of support out there for you. And on that note, feel free to take pictures of this if you'd like, but there are tons of great docs out there. The Power Tools docs is some of the best that I've seen in kind of the tech world. Some of the AWS docs are okay. They're not too bad, but they can get you started. And then, as I mentioned, those two articles from AJ I've listed on the bottom as well here. So he does a really great job explaining containers on Lambda and how to use them. And actually his talk on layers is exactly why you shouldn't use them. So it's a very interesting read. I encourage you to check it out. That's all I have for you today. Again, my name is Christy. I am a principal software engineer and serverless hero. My social medias are up here as well. If you are ever in the New Hampshire, United States area or the Belfast, Northern Ireland, we would love to have you join us at our user group. We are always looking for more attendees and more speakers. And on that note, we are actually running our very first Community Day event in Belfast in September. We just opened the CFP this week, so definitely check it out and send it to your friends. This is a free event to attend as well, so we would love to have you there and would love to learn from you all. Thank you.
Thanks, Christy. So we have a couple of questions from Slido. So the first one is, what happened to the servers when it's not being used?
Yeah, that's a great question and probably one of the biggest ones we get when talking about serverless. So AWS actually has all of their own data centers. So typically, it may or may not be in use by another customer of theirs. So they'll kind of spin it up as they need it. They have tons of different regions and what they call availability zones all over the globe. So they'll utilize kind of what's closest to you based on what's available. So you don't actually know the specific data center that your code is running with at any given time for security purposes and reasons. But it is probably in use by another company or individual that is using the compute and the storage there. So you can reserve it if you want. That's more with things like EC2, which aren't serverless, but they'll kind of dedicate that space to another customer or save it for someone else or something else later.
Okay, thanks. So another question. Any recommendation regarding which Python version to use on a Python Lambda? Namely, is Python 3.11, 3.12 working well there, or is it just supported on paper?
Yeah, I think, I don't know if you caught it, but on my talks, I'm actually using Python 3.11 in that one. So 11 and 12 are definitely, I'm pretty sure 12 is now supported. That is another kind of pain point, is having to manage your Lambda function versions. So they do a pretty good job at advertising when they're going to go out of date and when they're going to stop supporting it. One kind of gotcha with Lambda functions is that if you don't touch it or redeploy it, and like it's just out there being hit every so often, and it's 3-4 years old, and then that Python version goes out of date, you don't have to touch it; it'll still keep running. But as soon as you go to deploy it again, it'll prevent you from it unless you update your version to the latest. So that is kind of an interesting gotcha with Lambda functions, but they are pretty good at supporting the very latest and greatest out of the box, so you don't have to worry about that.
Okay, so another question. Can I use Python Lambda local to test local Docker images, which will be later pushed to ECR, or am I allowed to test only layers?
Yeah, I think that it is just, I don't think that you can use that library with containers. That's a good question. I might have to look at that. But you can with your regular function code. With layers, it shouldn't matter too much, like things like the Datadog layer, for instance. Like you might not even want to test that that's going straight to your Datadog metrics dashboard. So if you're like okay with kind of ignoring some of those pieces of it and just want to test like basic functionality, like in this case the data manipulation piece, it should still run. It might just not forward off to where you want it to go with the layers. But yeah, the containerization and the local testing is very, very tricky with Lambda and with AWS services in general still today.
Okay, thanks. So another question. How do you manage AWS Lambda's cold start and statelessness in Python?
Yeah, that's a good question. So I'll say out of all the languages, I think Python is actually one of the best with cold starts. They're very, very, very short or minuscule as far as Python goes. If you're using Java, that's kind of where you notice a lot of that cold start time going to. So it isn't quite an issue. If it's something that's kind of running continuously too, you're almost never going to run into the cold start problem. So you can do things like the containerization that might improve some of your cold start time, but it's usually not much to notice a huge difference.
Okay, so we have another question. Do you also use the serverless offline for local testing?
I do use the serverless, what was that? I'm sorry, you skipped it already. Was that somebody in the room that wanted to ask it?
I don't know, it's something in the room?
Yeah.
Okay.
Oh yeah, yeah. You can, yeah. So you can use it. I think you can use it offline. It's the serverless stuff is kind of like your whole architecture. So The Python Lambda local piece will only test the Lambda function piece of that. It's not going to like test your services end to end. I hope that they're working on something cool that would do that for you locally. The emulating locally is like one of the hardest parts, but it will help you test, like when we're thinking about like Python and writing our logic to kind of do those commands for us, it will test like your basic functionality that you kind of can do locally, but anything interacting with a lot of the deployed services is much more difficult. The mock events can kind of help with that, but it's not great, unfortunately. So we've been pushing on it for sure.
Okay, thanks. Now another question.
Okay.
How do you?
It's a marathon in here today. All right.
How do you usually deploy Lambdas on AWS? Any framework?
Yeah, there's tons of different ways that you can deploy. So I work in an enterprise, so we're a little bit stricter with how we can deploy. So we use things like Bamboo. But there are a whole suite of AWS offered services like Code Deploy, Code Pipeline, that you can easily hook into and deploy. If you don't have a ton of like enterprise restrictions and things too, you can also code directly in the console as well. So you can write Lambda functions and just click of a button, test them, and it'll work in that deployed environment for you too, if that's something that is available to you. And that's a really quick and easy way to get started. And then you can kind of move into this world more of infrastructure as code and utilize things like CDK, SAM, CloudFormation, and create these Lambda functions more in your code and in GitHub and deploy it up. So yeah, definitely if you're getting started with this stuff, if you're working with it on your own, I would check out some of the AWS tools and services that they offer because they have tons of developer tools available to you.
Okay, thanks. So a question on slide or over, if anyone want to ask a question. Otherwise, Christy will be available.
Yes, I will be here for at least
conference.
another hour or so, so feel free to come find me. I love to chat AWS, and if you're interested in community stuff at all, please let me know.
Thanks, Christy.
Thank you.
So we will have now a coffee break and then our keynote.
Please stay here, because apart from the closing notes, we have a raffle for the Apogeo books that we will give for free. So, go Apogeo. Thanks. Okay. Very pleased and honored to introduce Vicky Boykis for our last keynote. Vicky is a machine learning engineer at Mozilla AI, but for me and many others, she's much more than that. She has been through so many years as an inspiring and entertaining source of information for everyone trying to survive the constant innovation in AI space, making it feel familiar and approachable. She has taken the level of Twitter shit posting to such an excellence that they had to close down Twitter. At least that's what I decide to believe to whatever happened over there. She has a love for Italy, the Italian language, Italian pop music and culture, which I expect to be, and memes, which I expected to be fairly represented in the talk. She has flaws though. Up until now, she has never had a keynote in Italy. But we can fix that. So, let's please welcome Vicky Boykis.
Okay, is this good? Can everybody hear me? Good? Okay. Buongiorno a tutti. Grazie per avermi invitata a parlare. Avrei voluto fare tutto il discorso in italiano, ma lo sto ancora imparando. Per adesso posso parlare soltanto di gelato, o i colori, o cosa mi piace mangiare in Italia. Perché non so dire ancora, don't worry about LLMs. Il resto sarà in inglese. Okay, so a little bit about me. I'm Vicky Boykis. I work at Mozilla AI, which is a startup founded by Mozilla to do AI things. We're working on evaluating large language models. We're building platforms and tooling for that and open sourcing for that. By the way, all the notes for this talk will hopefully be available right after I finish it, and I can get Hugo to build correctly on my website. So while I've been building tooling for LLMs, what I've noticed is that a lot of the stuff is very similar to what I've been doing before. So prior to Mozilla AI, I've been working in machine learning for a number of years on recommender systems, on search systems, and on building ML platforms for security. And what I found is that both LLMs and these systems have a lot of things in common. So there's a lot of hype around them right now. But what it eventually boils down to is that these systems are just plain classical machine learning and classical engineering. So a lot of the time, around LLMs and AI, you might hear things like attention mechanism or LoRa. Really, a lot of what I'm doing is writing PyTest, building REST API endpoints, making sure unit tests pass, etc. Because the hardest part about AI apps is web development. So in that, how do we as practitioners cut through the hype and understand that you can link these two things together? And I don't know, but I heard a story here while I've been here in Florence that I'm hoping might shed some light on the situation. So I hear there's this really big company in Florence. It's called Medici Corp. They're very successful. They've been around for hundreds and hundreds of years. They specialize in banking, finance, art, and philanthropy. So they're very successful. They're international. But they have one problem, which is that they don't have any AI at all. Extremely profitable, absolutely no AI. So the CEO of Medici Corp has absolutely been worried about this. She's been reading a lot of stuff in the news about how you need to incorporate AI into all your applications. If you don't have AI, then it's bad. She thinks that this should be something strategic for her company. So she thinks that her customers should be able to chat with their data or do something similar. So what she did was she developed a task force, a small R&D team of developers that was built up, 10 or so. So there's SREs, machine learning engineers, there's a team lead, a PM, etc. And she said, go figure out something for us to do with AI, something valuable, and come back and report to me in a sprint. So these developers said, okay, I guess we have to demo something to the CEO. What are we going to do? So they decided to leave Florence because they wanted to really focus, grind, do JIRA tickets, get a sprint done, push this AI product out, and they needed to focus away from the city. So they went and they rented a house together. And they said, okay, now we're at the whiteboard. We're going to do AI. What are we going to build? They started doing some research, and what they saw was this. This is the current AI landscape. So there's a venture capitalist called Matt Turk that puts this together every year. And it started like sometime in 2012, and it just had Hadoop on there, basically. And since then, it's grown to this whole big thing. So there's open source infrastructure, there's tooling, there's libraries, there's cloud vendors, there's now LLM vendors on here, all of these different people. So the developers and the team looked at this, and they said, what? How do we build with this? What do we do? What do we even do here? Luckily, their team lead had some experience and said, in times like these, I turn to the wisdom of the elders. There's particularly one foundational thinker that I look at to guide me in times of great stress. And he said, in the times we live, a fundamental skill to survive is knowing what to ignore among the zillions of things presented to us every day, every minute, and in which things to focus our attention. Be picky as shit. Which is great. It's a great thing to think about, and it's a great idea. But then developers said, okay, well, how do we turn this into JIRA tickets? We have no idea. The question is, how do we actually deliver AI? So then the team lead said, the team lead was ready for this too. She's a really good team lead. She anticipated this. She said, well, let's look and see what other people have done already. There's plenty of engineering patterns that we can look at, plenty of blog posts. None of this is new. Let's look at what other people have done. Let's do some research. And what we're going to do is one person is going to tell a story per day on what they've researched. And then maybe we can make some decisions from there. And so developers groaned because not only did they hate doing research, but they also hated doing teamwork and presentations. But the team lead said, okay, just do it. Bear with me. We're going to get there. So then developers all went into their separate corners to do some reading, some research. And then they came together, and the first developer began to tell their story. And the first developer, the machine learning engineer, said, I've been reading about the bastaijos. And what it has to do with a single task. She said, what I've been reading about is medieval churches. So there's this church in Barcelona called Santa Maria del Mar. And what's interesting about it is it's the only church built in the Catalan Gothic style that's still remaining. And it took much less time to build than all other medieval churches. So a lot of medieval churches took around 100, 150 years to build. This one took only 55. Why? Because it was built by the community. So it wasn't the king or the head of the church or nobles that decided to build it. The neighborhood where it was located decided to build it together. And so it was decided that the nobles would contribute their money, and people who didn't have money would contribute their labor. And in particular, there was one group that contributed their labor, and that was the bastaijos. So these were porters, basically, who carried freight from the port of Barcelona to the city of Barcelona, because the port was a little bit away, and they needed to get to the city. So they were very, very good at carrying really heavy loads. And all they had was basically this little turban on their back, on their head, called a capsana, that protected them from getting cut from the stones. And these weight was really, really heavy, but they were really good at this. And so their guild said, what we're going to do is we're going to carry stones to the church. We're going to contribute by carrying stones from the quarry to the church. So the quarry in Barcelona is located at Montjuic on the top of a hill. You can see how high it is because you can see the rest of the city of Barcelona from there. And from the quarry to the church, right now it's like about a 15-minute walk. I don't know. I didn't walk it because it's far and I'm lazy. But back in the old days, you would also have to walk around the port. So it was like an hour and a half that you would walk from the quarry carrying these stones. So basically, they had this stone that weighed 40 kilograms. They put it on their back, and then they carried it all the way down the hill to the church. They left it there. Then they went back up and made another trip. And they would do this 5 to 6 times a day for many, many years. And then the architects would take the stone and then do whatever it is that people do to build really cool churches. Like they would chisel it, et cetera, et cetera. So while the machine learning engineer was telling this story, she paused and she said, wait. This reminds me of something. This is just gradient descent. And so gradient descent is a fundamental algorithm in machine learning which helps improve model predictive performance, aka how well the model does at predicting next items that it hasn't seen in its training data by making tiny adjustments based on how it did last time. So that's all it is. And it might help to illustrate this with a little bit more of a concrete example. Okay, so let's say we are a small artisanal producer of a hazelnut spread for statisticians, and this is called Nutella. Please don't sue me. So we produce Nutella when there's sunshine. We're motivated to produce Nutella when there's a certain number of hours of sunshine in the day. So we keep track of the day that we produced these jars and how many hours of sunshine there were. So you can see on Monday there was 1 hour sunshine and we were motivated to produce 2 jars. At this level you can see there's a pretty small relationship, but what we want to do is actually quantify that relationship. Let's say we want to know how many jars of Nutella we're going to produce next Monday when there's 5 hours of sunshine or 0.5 hours of sunshine or whatever. We want to quantify the relationship between the jars and the sunshine. So what we have is we have to create a formula for how we can predict the output. So the output is on the very left. We'll start from the left. We have the jars of Nutella that we produce. And then we have beta 0, which is just the predicted value, which is how many jars of Nutella we will produce when all else is 0. We don't really care about this as much because we care when there's more hours of sunshine, but in general, yes. And then we have our actual hours of sunshine, which is x1, and then how important that feature is, so how important the weight is. For us, it's pretty important because it's our only feature, but in larger equations where you have more features, you'll have different weights. And then we have an error term, which is a residual, or the difference between the predicted and observed values. So really what we're trying to do is we're always trying to predict y based on all these other inputs, particularly the weights and beta 0, which is the bias. And we're always trying to make epsilon, the error term, smaller. That's all we're trying to do in this equation. How do we make it smaller? We want to minimize RMSE, which is mean squared error. So the way we do that is we have the actual hours of sunshine and the predicted hours of sunshine. We do some math to it, we square it, square root it, and we have the actual formula on the left-hand side, and we're always trying to make that smaller. We're checking the difference between what we predicted and the actual values, because we have actual values before, and always trying to make that smaller. What do I mean by always? We're descending the gradient in a loop. So this is kind of Python code, it's kind of pseudocode. It's like somewhere a mix between the two. So we start by initializing our weights, which remember we had 1 hour of sunshine, our bias, which is 0. And then we have this thing, costs, which is all the iterations after we calculate mean squared error. So we start with our equation on the first line in the for loop, and we say we have this number of iterations. For our purposes, we can pick 10 or 100 or 1,000, however many we would like to get our cost to converge, aka get to a value that we're comfortable with. So then we do the prediction of the predicted y, and then that's our cost. And then we add that to the costs, and then we go through the loop again. If it's at or below the threshold that we'd like it to be, we stop. Otherwise, we keep going. We calculate the current weight. We calculate the derivatives, weights, and biases, and then we append those to the equation. And we keep going over that again. And so at the end, what we have is this list of costs. And if you look at the list of costs over the number of iterations, what you can see is we have a slope of a curve, which looks a lot like the elevation descent that the Bastajos made when they descended from Montjuic to Santa Maria del Mar over and over again. Because gradient descent, as Sebastian Reuter says in this really great paper, is basically the art of going downhill until you get to a point that you're satisfied with. That's it. We follow the direction of the slope of the function until we reach a value. So the developers all paused, looked at this, and said, we need to be Bastajos. We need to focus on one thing when we want to create the software that builds AI, which is really hard because large language models can do millions of things. They can do translation. They can do QA. They can write you poems. They can write you a talk in the style of someone else. They can do all these things that are on this and a lot more. How do you pick, when you select a large language model as your tool, how do you pick it to do one thing? Because it's meant to be general purpose. And the answer to that, the developers said, is to look at your actual business problems. What business problems do you have? Do you have a question answering problem? Do you want to do translation? Do you want to do word completion, etc.? And a good heuristic for that is the 1,000 interns heuristic, which I've heard of, and I link to the source once I have the notes up. But basically the idea is if you have 1,000 interns who are reasonably smart people but have no context about your business or your problems, and you sit them in front of a problem, and you give them a small set of instructions, would they be able to do it? If the answer is yes, then you can make an LLM do that. It's a perfect use case for that. So some specific use cases are translation, topic detection, summarization of documents, classification, and named entity recognition, so recognizing the words that you care about in any given text. So the developers and the team all got together. They thought about this. What use cases do we have that actually might require machine learning and LLM specifically? And they thought that they have a lot of documents relating to sponsorship. As you know, they are very much patrons of the arts. They have a lot of artists, the Medici Corporation, that they sponsor. There's a lot of documents floating around. And what they want to be able to do is pick out topics from those documents that they care about to get a better sense of the landscape of the artists that they're sponsoring. So for example, if they have a bunch of topics related to Michelangelo, a bunch related to Botticelli, and a bunch to Da Vinci, they want to be able to say that Michelangelo is related to statues. Or they want to say that Botticelli is really into myths, and they want to pull that and do analysis on it. So they thought about this, they came to a conclusion, and they presented it to the CEO, and the CEO was very happy. She said, topic detection, great. When can I see this model? Can it be yesterday? So they had their first solution, but now they were ready to move on to the next step, and they were still doing research. So then the second person got up to tell a story. And the second person said, I've been reading about medieval monks. I don't know why, but that's where my research took me in that direction. She said, I was reading this book called The Wandering Mind. It's by a historian called Jamie Kreiner at the University of Georgia, who does a lot of research on medieval type stuff. And she was really interested in how monks find focus, because that's all medieval monks wanted to do. They wanted to get to a point where they're concentrating really on praying and on their spirituality and kind of shooing away anything that has to do with daily stuff. The problem is, even in the Middle Ages, apparently there's a lot of daily stuff going on. Like I don't know, I'm just speculating here, like livestock trades, gossiping, I don't know, creating weird manuscripts, etc. So even in the Middle Ages, people had the same problem of they could never concentrate on the one thing they could concentrate on, even though there were no phones or anything like that. And so there was one medieval monk who wanted to concentrate so much that he went from Europe to what is now Egypt and Israel, in that area, and he lived there for 25 years because there were a bunch of monasteries in that area. And he went around to each monastery and asked, how do you concentrate, guys? How do you concentrate? And then he wrote all of that down. And even he said the mind keeps getting pushed around by distractions. Now, back in the day, they thought this was basically demons that did this, not the iPhone. But you know, it's like kind of the same thing. And what these monks found was that they needed to create the right environment because they knew that these distractions would always be constant. There was no one solution for how they could show away these distractions. So they did a bunch of stuff. Like some of it was weird, some of it was cool. Like some of them went to live alone for years and years and try to meditate and get to a higher level that way. Some of them didn't bathe for a number of weeks. I don't know how well that went for them and the people living in the monastery. Some of them ate only certain things. Some of them meditated in nature. But the point was they knew that this required kind of a system of things because the human brain can only concentrate on one thing at a time. And so there was another monk called Hilmar Sivatai that said, it is impossible to focus on two things at once. And later, science actually proved this with a study by George Miller, which Feline Hermans wrote about in The Programmer's Brain, which is a wonderful book. I strongly recommend it to everybody. And said that humans can only fit 7 + 2 things in memory, and really less than 7. So if you get to the point where you have, if you think about like a grocery list, if you get to 7, like you have a push and it clears the cache because you cannot think about any more than that. And really the best way to do this is to concentrate on one thing. And so when the developers looked at the LLM system that they were building, they saw that it started to get complicated immediately because first they had to pick an LLM to use. So that would involve either an LLM API or their own model. If they had their own model, then they would need to create storage for the model. They might also need a vector store if they were doing embeddings or RAG-based search. If they were serving it, they also would need a model engine and a model server to stand all of that up. They would also need a UI, and regardless of whether it was on-prem or they picked a vendor, they would need prompt optimization. And as you see, like this starts to get complicated very quickly because then you start having a number of different questions that are concurrent in your mind, like which API do you pick if you're using an LLM vendor? If you do this, do you build or buy? Do you build the vector store? Do you buy the vector store? Which cloud storage do you use for any of this? What kind of latency do you care about? If you're hosting a model, are you now using Kubernetes? What's the throughput of, etc. So there's a lot going on, and they thought about how do we break this down to one thing? And then the developer telling the story said, this is really just about Unix. And what they meant by that is the philosophy of Unix, which says that each program, regardless of what we build, should do one thing well. To do a new job, build afresh rather than complicating old programs by adding new features. That's the philosophy of Unix. How does this square with the fact that machine learning requires quick feedback loops? As you saw in the gradient descent example, we're always looking at our data, we're looping over it, and then we're comparing. We're comparing the old value and the new value, we're seeing if it's better, we're doing another iteration. Then we're comparing the old and new again. That's very different from the way we traditionally develop software, which is just we build one thing that makes a button green, or we build one thing that writes data to the database. It's very, very non-deterministic, and it's very, I don't know, like hand-wavy and vibey and etc. Which is why if you're a project manager and sometimes you go to your machine learning engineers and they're like, when is this going to be done? Well, we don't know. What does it mean to be done in machine learning? It's very much an iteration-based cycle. So the difference is that in machine learning, we start with data and learn the rules. When we create a traditional application, like a CRUD app, we start with data, or we start with our rules, and then we build to the answers. So the way machine learning works, as I said, it's very circular, and it's also more like alchemy, which is actually the title and the content of a talk that two famous researchers gave in 2017 at NeurIPS, which is a machine learning conference. They basically said it's like alchemy because we're constantly looking at what we have, seeing if it makes sense, and then throwing more numbers against the wall, seeing if it makes sense again, tweaking this, tweaking a hyperparameter, and seeing if it makes sense again. So how do we focus on this one thing? How do we get to a system that does this one thing well? And the way to do that is to get to a state where you're constantly evaluating your LLM use case and focus on that as the endpoint. So how do you do that? You can evaluate large language models or any machine learning model, but particularly large language models in two ways. You can do a vibe check. I stole this from Zach Mueller, who I thought had a really good one. It's basically like, oh, you look at it, oh, it looks good to me. Okay, great. Or you can look at offline metrics, which is basically an aggregated vibe check based on statistical reasoning and properties that academics have looked at for benchmarking. So there's a bunch of offline metrics as well. The ones on the right are particularly for trending topic analysis. So there's purity, there's cosine similarity, and there's dot product, which I'll get to in a minute. So let's think about the vibe check first. How do we as humans decide what trending topics are? So here's Michelangelo's Wikipedia page. I just copy and paste a lot of it. There's a lot of words in here, blah, 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 sculptor, blah, 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 classical antiquity, blah, blah, sketches. So your mind kind of pulls out like what you think the top topics are based on your domain expertise. And your domain expertise is you work at the Medici Corporation as an art philanthropist. So you already know this word, you know which words are the most important to you. And so you pull them out kind of like in your mind. And you say, okay, here's my text, here's my original text, and here are the topics that I think are most important for this piece of text. Now what you do is you feed it to an LLM. And in this case, I'm using a local LLM, using Llama which is a wonderful project. And basically, it lets you run an LLM in a single file on your local machine. You can also run on GPUs, but I just run it on CPUs in my Mac. And so for this case, I'm running Mistral 7 binstruct v0. I know we're at v3 right now, but etc. So what you do is you create a prompt, and you feed it to the LLM, and you let it answer it. And so for this case, it says you will receive a document, top-level set of topics from a hierarchy. The goal is to identify the missing topics, and like you have to yell at the LLM a little bit, like don't stray, don't do weird stuff, please just pick from these sample topics, etc. And then you have your instructions, and you can just run this locally. That's another part of focus, is you can run a local iteration loop very quickly. And then the LLM will come up with some topics for you. So then what we do is we compare the human vibe to the LLM vibe. Do these look kind of like they make sense? Yeah, kind of, I guess. As an art expert, I probably would think that Renaissance art, sculpture, painting is general. Like, I mean, everybody's doing a Renaissance now. That's old news. So we don't want that as a topic. Art, okay, yes. All of these are artists. We don't want that. Sculpture and painting, maybe. Music, we don't want as a topic. So we can already see that the first pass at what this LLM gave us is not really good for what we want. It's not really a solution for our problem. So then we get into levels of modifying this. The first level we can do is prompt engineering, right? So for example, we might yell at the LLM a little and say this topic should only be related to art and more low level than Renaissance. Do not give me Renaissance. Then we might cross out Renaissance because it picked it, because it saw it in our entry text, and pick sculpture instead. So there's tons of tweaks that we might do like that. Remember, again, we're iterating. So we might have to iterate through the prompts. We might have to change our model depending on what we have. We might have to fine-tune our model. We might have to do a lot of different experimentation. But what we always have to be doing is evaluating the results of these things, and doing that will get us closer to what we actually want, because most likely, if we're doing something specialized, we will not get to it the first time. And then there's formalized metrics that we can do, the offline metrics that I talked about. So there's cosine similarity, which looks at the topic similarity between trending topics in clusters. So we can cluster it and then evaluate it that way. And that'll give us something more automatic than just a vibe check. And there's a lot of these different types of metrics. So they evaluated it. They got to a model that they liked. And then they showed it to the CEO, who said, I love these generated topics. Great. When can we see this in production? So now they had step 2, but they still had one more place that they needed to focus on. Now they picked this model. They picked an open source model. They wanted to host it locally because they had compute, because the Medici Corporation has a lot of compute and its own cloud, etc. Great. So they have this model. They have a production. They have a UI for it. But as soon as you have a model, now you have an LLM application, and you have this horrible thing known as LLM ops, which is just like ML ops, but more. So you have 5 million different things that you now need to be monitoring. You need to be monitoring the performance of the model, of what text it outputs, because remember that LLMs are not deterministic. They're also going to give you, depending on how you set your hyperparameters, different answers every time for this stuff. They might give you weird stuff. They might give you bad stuff. They might give you stuff you don't want. So you have to monitor that. Then you have to do classical engineering monitoring, right? So if you're running this on K8s in a distributed system, you have to monitor all of that, all of the storage for it, etc. So you start from something very, very focused, which is we picked one model for one task. We evaluated that model. We know it performs well, but now it's exploded into an engineering system that we now have to handle and control. And so they did their reading again, and the third developer spoke out and said, I've been reading about Ellen Ullman, and a reproducible example. Ellen Ullman is an author who was working in tech in the 70s, 80s, and 90s. She's a wonderful essayist. I find a lot of the stuff that she writes is very relatable to tech today, even though she was writing for what is now back in the day. And she has a lot of essays. And one of the essays she turned into a book. There's a book and an essay. There's an essay called Closer to the Metal and a book Closer to the Machine. And her whole point in that is that as developers, we need to be working closer and closer and closer to the part that's more important. And the way she said this was low-level code or anything low-level in real life is bad. Anything that is in programming that's low-level is better because it means it's closer to the essence of what we actually want to develop. I don't know about the part about money and prestige, but in general, it's good to write code that machines and other programmers can understand and to be able to make it testable. Because when you do that, you really get to the heart of the problem. You're working on things that matter. And she was talking about this in a very general sense. I find that it applies today a lot to cloud programming, where you're copying together different components and trying to glue them together, etc. A lot of the times it's untestable, especially if you have distributed systems that you're working with. You often end up needing to rerun things a million times just to replicate the condition, and you can't clone S3 onto your local machine, so then you don't know the behavior of S3. There's actually just like a recent story about how they were charging for basically 404s to URLs. So you can't test that. You don't know the behavior. What do you do? So the answer is kind of to like write code in the old days, where you basically just had you and the machine and a million bugs, obviously. And then you had books and guides to read. So kind of like a similar thing would be working locally today and only using python.org, which is not a very good user experience, but it does make some things a lot clearer for you. So let's say that you can't do that. Let's say that you're working, as most of us, in cloud environments where you can't reproduce things, you can't test some services. What do you do? The goal is to get as close to a reprex as you possibly can in order to get to good, clean code. And a reprex is a concept from the R community, so from the R software community. And the idea is that a reprex is a reproducible example. And they created this term because a lot of the time they work in R or R Studio, which is a single piece of software, so it's a little bit easier to do reprex in that environment. But the idea is that you want to have a small snippet of code that can run on somebody's computer, that can be extremely easily tested, and that you can just pass off and say, okay, it doesn't work on my machine, Well, it doesn't work on my machine either. So what are we going to do? Now we can fix this bug. What's an example of a reprex that I talked about a little bit earlier? It's root mean squared error, right? So you have one method call, you pass in floats, you get out floats. It's going to work the same in any Python, maybe, I don't know. I'm getting into a hotly gray area here about Python environments, but this should work the same in any Python environment that you work in. And you can give it to someone else and say, why is this working or not working? So in that way, it's basically spiritually similar to a unit test. And so they said, okay, well, what is one way that we can test this? So the developers decided at the time to use Ray, which is a Python library for distributed computing. It's a spiritual successor to Spark in a lot of ways. It's used for a lot of large language model training, sometimes serving at this point. So it's also a lot like Dask, except particularly in the large language model space. And they decided to use this to serve the model that they had chosen and selected. Now, Ray is really, really complicated, like a lot of really distributed systems. So there's a number of orthogonal, sorry, I said orthogonal, but there is a number of orthogonal points happening in Ray. So first is the design of itself, where you have a task and an actor. So it follows the actor pattern of where you have stateless tasks that are sent to a given Ray cluster, and then actors, which are stateful applications. So first you need to understand tasks and actors as the first starting point for an array cluster. Then you also need to understand that these tasks and actors run on a driver, and you have worker processes happening. Then you also need to understand all the potential parts of an array cluster. So not only is there a head node, a worker node, however many worker nodes you have, once you add more, you add an infinite number of complications. Then you also have the global control store, which is kind of confusing the first time I saw it because it's GCS, and I thought it was sending all my data to Google Cloud Services. And I'm like, what is happening here? But it's the global control store, which controls all the state. Then you have a scheduler. Then you have an object store. There's a number of different paradigms happening in each stage of Ray. So when you pick it, it's really powerful. But remember that humans can only do one thing at a time. They can keep one thing at a time while in memory. And when you're working with Ray, you have this whole messed up little cake of things that you have to have going on in your mind as a developer, right? So first you have the Python fundamentals, because you have functions, you have classes. Then you have the actor pattern on top of that. Then you have your deep learning model architecture, which you have to understand how that works in order to be able to load it in Ray. Then you have, like I said, the Ray actor model. Then you have how all of this acts on GPUs, because that's very different from how CPUs work. And moving data from GPU to CPU is also very, very different. Then on top of that, you have, oh Lord, Kubernetes. So then you have Ray, which is a distributed system, running on Kubernetes, which is another distributed system, possibly running on a cloud, which is a third distributed system. And now you're in hell. And then on top of all of that, you have your Python environments, which you also have to keep track of. Okay, so now that we know that we have to keep all of that stuff in mind, let's serve a trending topic model. So this is using RayServe. And essentially what RayServe does is it uses this actor pattern to set up what is essentially a web service, a long-running web service. It has a REST API server. It has ingress. And then you can replicate it, because the whole thing with Ray is that it can work on multiple nodes. How do you set one of these up in production? So there's a number of ways you can work with Ray, and one of the really cool things about Ray is you can run it locally. So that already makes your feedback loop faster, because you can run it on a single machine. And I believe you can also now run it in multi-cluster mode if you tell your Mac to do bad things. So then we have this RayServe config file. Now we have YAML, yay. So the way you serve it is you specify your application name, where you import the path from, the deployments, and then all the regular Kubernetes type stuff, so the number of replicas, health checks, CPUs, GPUs, et cetera, et cetera. So this is good on the one hand, because what it does is it ships your working directory, whatever you specify and whatever you bundle in there, to the cluster. So what it does is it takes that, it takes it as a zip file, and then it ships it to the Ray cluster as a working directory. However, because ironically YAML tries to simplify things for you, it actually creates more complications, because if there's a failure point in serving the trending topic model, as the developer saw, it can fail in any number of different ways. It can fail in the import path. It can fail in the working directory if you specify it from a pin git hash. It can fail in the pip import if you specify the wrong version of machine learning library, because they're often quick moving and sometimes in conflict with each other. And then it can also fail in Kubernetes, etc. And that's exactly what happened when our developers tried to serve this model, and it didn't work. And there was a failure in the package imports, and they were like, okay, what do we do? Like, which part of the cake is this a failure in, even though it's giving us an error message? And so what they saw was that the package is trying to do a relative import. This seems like an easy Python error, and maybe it is, but now we have to look through basically all of Ray to see what's going on here. So we have to go through all of the levels of Ray internals. So we have to look at the dashboard, which interestingly enough is where a lot of the key Ray code is stored. Then we have to look at if it's an error in Ray serve. Then we have to look at Ray core. Then there's multiple languages that make up Ray core, so then we have to look in Ray Python. And finally, when we dig through all of that, what we see is it's in this file called _private/utils.py. And what we have there is the code that now we can finally reprex. So this is actually from that utils.py module. This is the code that does the import of the directory. And so what they did was they isolated just this method. And what they did was they started to call it. So first they called it with this path, and that didn't really work for them. And then what they saw was if they didn't have a relative import, if they just had the exact import as is, this actually worked to serve it. So what happened here was they were able to isolate the problem, go through all of the layers of Ray, and get to a point where they were able to offer a solution. So now what happened is that they had a trending topic app, and now they were serving it in production. So now they were happy, they could go home. They did this all in 2 weeks, by the way, but they were celebrating. They said, okay. Of course, their celebrations didn't last long because the CEO came around and said, I love that this is in production. When can we do more? Because success means that they can now do other things with LLMs. They understand all the basic patterns that this gives them. They understand where their errors are, and they understand where to go from here. So they got together in a retro and said, okay, now we have to build another LLM-based application. What are we going to do? Where are we going to go from here? And they realized after reflection that they have to take these three things into account. So how do you actually stay closer to the metal? How do you get to the point of what matters in building, particularly in a time when we're working with large language models? There's a lot of AI flying around, a lot of hype, a lot of different terminology, a lot of people trying to sell things. How do you get to the point that actually matters? And it turns out that the answer is that it's still the same as general machine learning and as general engineering. The goal is to pick a single task. In machine learning in particular, this means for LLMs, picking a single task that you want your LLM to do. So if you are, for example, MetaCheat Core and you're trying to get it to identify trending topics, you don't care about it writing poems, and you don't care about solving reasoning problems. You care about this very, very specific use case. And that's why a lot of people are now actually going into smaller large language models that are more trained or fine-tuning their data sources for this task. The second thing is to pick a measurable goal. And you can do that in one of two ways. One is to do the vibe check with what actually resonates with you and your business. And again, sorry about this, but stakeholders. And also do this in a reasonable way. So if you're a company that is serving a SaaS product, do A/B testing. See how this performs in testing. Do internal testing. For example, Databricks had people in Databricks actually label the data for the model for domain expertise. So do that as well. So pick the smallest measurable goal and do both offline and online metric testing. And finally, from an engineering perspective, you're going to be working with a lot of different pieces, as we already all are. We have a lot of different libraries working together. We have cloud, non-cloud, on-prem. We have different services. For testing, pick the smallest piece of code you can possibly get to and try to reproduce it locally, because that's going to save your sanity. And once you do all these things, that means you will have moved closer to the metal. Thanks, everybody. Thank you.
Thank you, Vicky. Sorry. Okay, so we'll now take questions. As usual, you can put them through Slido with the Lasagna room. There are no questions at the moment in Slido, so we can do them live. Ah, in the keynote, sorry. It's the first time I do that. Of course, it's not working for me at the moment. Okay. Okay, so we'll do it the old way. Who has a question for the moment? While you think a little bit for the moment, so we have this, I can start to break the ice. We have this situation in which now many Medici corporations are asking everybody to do AI. From your point of view, do you see that there is an escape to this, or is this something that is going for quite some time?
I think there's going to be, it seems like now there's an inflection point where, is my mic on? It is, right? Yeah? Is it on?
Yeah.
Hello? Test.
Okay. How are we doing with her microphone? Mine seems
Test.
working fine.
Test.
Otherwise, I will
Good?
give you mine.
Oh, good. Okay. Okay. Yeah. So I think we're at a point right now where, like, the last year was everybody trying to do everything with AI, but now we're narrowing and coming across actual use cases, which is actually why I came up with this idea for my talk, because there's a lot of stuff that really does deserve or need these types of models, like summarization, for example, as I said, topic detection, etc. There's a ton of good places where you can actually, and it might make sense to use these models. So I don't think it'll go away, but I definitely think it'll be much more focused going forward.
Okay, so we start getting question. The first question I have here are, what are the most important projects by Mozilla AI?
Yeah, so the first one that we have open source and shipped right now is LM Buddy. It's a platform and library and framework that allows you to evaluate and fine-tune large language models. So you can look it up on GitHub. And we're also working on developing a platform to do similar things. Stay tuned for more on that.
Okay, thanks. The next one will be, will it ever get simpler?
No, I don't think so. I don't know. People who have been in this career longer than me can tell you that whether it will or not, I think we will get to a point where we're at like higher levels of abstraction, so you don't need to know the levels below it as much. I don't think, like, I think once cloud started, it really couldn't get simpler, because almost nobody, there's like 5 or 6 companies that are moving off cloud, but nobody's really moving off of it. But the thing is that you have the power as developers in your organization to push for things to be simpler. As technical people, we have the power, and I say responsibility, great power, great responsibility, etc., to push for solutions that are simpler and say, hold up, wait, let's try something else.
Okay. There's a very specific question about LlamaFile. Yes. Is LlamaFile a project by Mozilla AI? What is its main purpose?
It's a project by Mozilla. So parent company, Mozilla. And the main purpose is to allow hobby developers or anybody who doesn't have access to GPU cores, just really anybody who doesn't want to use or can use GPUs, to do things locally. And more than that, it's a project to allow you to do everything in one file. So it's literally one executable that you download, and then you download the models that you want, and you use it with that. And it also has a web server. It's great. I use it a ton for prototyping different stuff with LLMs, because you don't need to pass an API key. You can do everything locally. I could give like a whole talk about Llama and Justine Tooney's awesome work on it. But yes, if you want to play around with it, it's a great, great way to do that.
Okay. The next one is by Nicolas. If someone wants to get up and say their question, I can go and get you, but if not, in the meantime, if you can turn it on again. Nicolas is asking, what about the next NormConf?
No, next question. No, I don't think it's going to happen anytime soon.
So for those who don't know, NormConf was a great conference that was organized by Vicky. And okay, and other questions? I don't have them at the moment in this app, if I'm able to operate correctly, but I think I am at the moment.
There's a question.
Yep. Okay, thanks.
So what do you see as the utmost big problem in AI? Like what is the biggest challenge you see ahead?
I think, honestly, finding the right use case that makes sense for your company, for whatever you're doing locally. And which I think is why I gave this talk. Like, basically, you need to find the thing, because it's so broad, and there's so many choices. And it's like, do I use local models? Do I use OpenAI? Do I use Anthropic? Do I use this? Do I use that? So it's finding your use case and really narrowing in on it, because there's a lot of noise, and it's really hard to understand like who's talking about something genuine or who's talking about noise. So all of that.
Okay. Yep. Another question over there.
Thank you for the keynote. I had a question. We've been working with LMs for a client of ours, but since we're from Italy, we always struggling with the fact that basically all of these models just excel at English, but then there's the rest of us, right? How do you think we could mitigate and lower the barriers for those models and this application to be useful and produce like reasonable results in other languages, such as Italian?
In other languages? I think possibly the best way is fine-tuning. Like, I know there's at least 3 or 4 different Italian fine-tunes going on right now, like Lamini. There's a couple other ones. But I really think like for language-specific things, because the current wave of models is supposed to be general, English language internet, etc. So really like the best way to do anything with machine learning is to get better data. So, and that involves like data specific to that language for including sites that like maybe, I don't know, the original model builders didn't consider, like specific subreddits or newspaper sites, etc. So the best way is to just get better data in that target language.
Okay. Another question.
Thank you very much for the keynote.
Sure.
In the last month, I've seen the knowledge of how to design a software system around large language model more and more valuable. Do you have any good research to suggest in order to learn generative AI system design, so to call it? Thank you.
Like I said, a lot of what I do is build REST APIs. So if you know how to build REST APIs, that's like 80% of it. Less blasé, I don't know offhand, because it's such a new topic that there's not really anything concrete to that. I know a lot of different posts, but there's no canonical resource for it yet that I know of.
Okay.
Okay, you mentioned Rust. So I have a question. Do you think that more and more Python libraries will have Rust in its backend?
I don't know. That I have no opinion or expertise on.
Okay. Let's see if someone else has other questions. Yes.
Thank you, Vicky. In your story, do you think the CEO got a bit lucky with the results?
In what way?
Well, of a number of CEOs, how many of them would be likely to have come up with something that did seem to be producing value from them going down these paths? And how many of them do you think would have barked up the wrong tree completely?
I mean, I think it's common in machine learning in general, right? Because it's very iterative. We don't know how it's going to work. At the beginning, it's very murky and very research-based. So in some senses, yes, but a lot of it was the team, the team's work, right? And finding out really what mattered and focusing on that part. So I don't know the answer, but yes, machine learning is very non-deterministic, and a lot of it involves a lot of very, very focused research. Yep.
So a follow-up question to this. So when you take an original, like a classical engineering team that can have a known velocity, how do you build safety and predictability in new AI ML teams?
How to build safety, and so how to maintain velocity, I guess, is the question?
Team safety.
Team safety. Okay, so are you talking about like the fast pace of iteration with this? Well, I think it's up to like the team lead here, to kind of push in both directions, right? I don't know. I'm not an expert on team leads, but I think like what I've seen in places where this worked really well is that the team lead pushes up and sets expectations, saying, look, this is a new area. We're entering an R&D phase. We're going to be a little slower for a while until we figure out. We're going to give you regular feedback on our cadence, but you have to understand that for us, this is completely new and greenfield. And if you want like regular updates, yes on those, and then to push down and say, okay, here are the expectations on here. So maybe it's not up and down, it's just like you have to communicate in both ways. And like really the only answer is open communication. That's the only way to make sure that the developers are not working in the dark and leadership understands what they're working on.
Okay, other questions? Yes. Thanks. Okay, so how can LLMs balance effectiveness with ethical considerations?
Yeah, so this is part of the research cycle. So I guess I'm not entirely sure what the question is, but if I had to interpret it, I would say maybe an LLM is good, but it's not fair for whatever definition of fair we decide is important to us. So how do we balance that? And the answer depends a lot on like the culture of your company, the culture of your team. From a personal perspective, I think it's important to, like I said in the previous answer, communicate and share and do a lot of testing. Because there's a lot of different edge cases with this. There's a lot of times when LLMs have said weird or bad things. So before you launch a product like this, really consider that and then set the expectations that, again, this is non-deterministic and it might produce wrong output.
Okay, we have another question from remote. The pyramid of what one needs to know keeps growing, it seems to me at least. How do you stay on top of all the technology? Any tips?
Yeah, so I wrote a blog post about this, so you can check on my blog. It's like how I learn machine learning, vickyboikis.com. That's one way. So what I wrote in that blog post is first, you need to develop a broad base of general good engineering skills, because that's going to take you really far no matter what area you work on regarding this engineering fundamentals. Once you learn those, like the space keeps growing, but it's really not, because in some senses, like, oh, okay, we built a cache. Well, a cache is just a Python dictionary. It's just X. It's just Y. So these concepts all start to relate to each other as you gain mastery over all of them. So it's really not like or for example, like LoRa is a new fine-tuning technique for large language models. Oh, okay, LoRa is just a type of fine-tuning, which works on all machine learning. So you start to kind of like, it's big, but it's not as big because you understand the fundamentals. So yeah, but the long answer is that blog post.
Okay. If no one else from the audience has any questions, let's thank Vicky again.
Thank you, everybody. Thank you for coming. Thank you.
And now,
I mean, I know, unfortunately, the books are in Italian, but I mean, it can be like a motivation for starting learning Italian if you're not. So if you wanna pick a number, then we're gonna do the raffle, and in the meantime, we are gonna start the closing session.
Now with more enthusiasm.
I'm tired. All right. One number, just pass the box.
Give me the box.
Yeah, pass the box.
No, I had
the whole box? Cesare, come on. You don't need the books. You don't need the books. Yeah.
Okay, just a quick surprise now. Yes. If it's a surprise, you don't know because it's a surprise. Okay, so after the closing, just after the closing, maybe you have seen around these days the cameraman, always the camera around. He was doing some kind of a documentary on the work group of PyCon Italia and on the Python Italia Association. So after the conference closing, only for you here, we will see just the first result of this documentary. A few seconds. Are you ready? Yeah. It will be epic.
Okay, I didn't know that. Yeah, even if I'm part of the thing. Wasabi. C? No. No. Wasabi C. No. Okay. Did you pick numbers? Is there... All right, so what's the plan?
Go with your thing, don't worry.
Okay. So I guess this is the last bit of PyCon Italia to 2024, and we just want to say thanks. So now we're going to start with a few numbers. We have had attendees from 40 different countries this year. So and this is the top 10. Surprisingly, the Italian people were the most, but I would say that we are basically arriving to the break-even point because we are basically most 470 people Italian, and then the rest of the other foreigner from outside Italy. So we were 833 people, and 470 were Italian. So it means that we had a lot of other country representation in here, and it has been a very great progress so far. We have had roughly 120 sessions this year, so I mean, it was pretty intense program, I guess. I don't know how did you feel about that, but to me it was intense mostly to organize the whole session of talks. We had 6 keynotes, and thank you again for being part of PyCon Italia 2024. Daniele, Vicky, Jody, Messina, Antonio, that is not here. Who I forgot? Daniel Roy is not here as well. No, Daniel, I mentioned him. He's in front of me, he's staring at me. So thank you again. Lightning talks this year. I mean, thanks to Valerio and Alessia and Matteo that ordered the pizza spin wheel on the Amazon to. What? Just paid, yeah. I mean, you clicked it on the thing, yeah, the thing, you did the thing. And thanks, Carlo, for monitoring all the expenses that Matteo does every year on Amazon. Pretty useful role. But this year, I think it was a success, and I believe that next year we're gonna have much more fun, and in my opinion, we should have lightning talks every day. Spoiler alert. For the pizza. What? For the pizza. Yeah, exactly. Yeah. Maybe next year is not gonna be a pizza. It's gonna be, I don't know, another thing. Yeah? Tigelle. So we had 2 social events. I think it went pretty well this year, because if you have been here in 2023, the pie drinks, it didn't go so well. So yeah, we forgot about that. So, but I mean, I think it was a pretty success. I mean, in my opinion. So, yeah, for extra workshops this year on Wednesday, yeah. Humble Data, Django Girls, part of the representation is here. I see the yellow t-shirts over there. Beginners Day and the public speaking workshop. We had the Lego contest. The winner has been announced on Discord. We already gave the prize to Rodrigo. Is Rodrigo here? Yeah, he's the winner. So do you confirm you have the prize, right? Yes. Okay. And so now I would like to thanks a specific representation of the organization. So the volunteers, thank you. Every PyCon is not possible without volunteers at all. So a big thank you. Alessandro and Matteo that takes care of the photograph and the video and all the social aspects. Matteo is over there. Alessandro, I don't know who. Where is Ale? He's filming, of course. Gonzo Design and TopX for the recording session and the streaming session over there and in all the room. They have been part of PyCon Italia since forever, basically. I mean, I do remember them, like, I don't know. We were like... I always remember Vincenzo's bird, so yeah, that's fine. So thank you for the sponsors. Yeah. Every year we need money, otherwise we're not gonna pay the venue. So that's basically it. The pizza thing. Yeah, the pizza thing and the Lego bricks. Yeah, you know all these funny things. So thank you to sponsors. Thank you to speakers, of course. And thank you to you, to all the attendees, of course. This is basically the first day we're with Alessio and Esther going. Giovanni and Gaetano that did the presentation. Esther, Valerio, sorry, guys, I'm screwed up. So thank you to the organizers and the staff. So please, all the yellow t-shirts, come on the stage with me. Yeah, Tiago, you're part of it. I mean, I teased you, but you're now part of the staff. Pietro. No, Pietro, vieni su. Marco. Dai, cazzo. Thank you. Thank you. Sit down, please. Okay, so a big announcement, I would say. You know? Yeah. Okay, the new days for 2025. But actually, first, I would say, where it's gonna be? Any guess? Yeah, Bologna. So we're gonna leave Florence to get a new, a big place, a big venue. So hopefully we're gonna basically sell more than 133 tickets, probably. And when it's gonna be in the Savoy. Sorry. Yeah, I know. Yeah, see you next year. So it's gonna be from the 28th to the 31st of May, and it's gonna be again from Wednesday to Saturday. And where, of course, Bologna, the Savoia Regency Hotel. Savoia Regency Hotel is a huge structure, and it's gonna be all ours. Okay, so no other people there. Everything has been reserved for PyCon Italia, including the hotel. And probably the lightning talks will be hosted by the swimming pool, and I mean the jokes are actual swimming. So yeah, this is basically, I mean, we want to show you the swimming pool, actually. That's the thing of the slides. But the conference center is pretty huge. We have a lot of spaces. The plenary, the main room is huge. And so we can maybe fit more people and avoid to refuse selling tickets to the people after the sold out. So again, we would like to thank you, and we would like to hear from you. We're gonna send an email with the feedback form afterward, and we have a board. There is still a board outside, or yeah. So we have a board outside. If you like, we can you can leave a message for us. Yeah, because we keep the paper every year. We store it in our storage room every year. So we have plenty of that from the past editions. So the feedback form, I told that. So yeah, thank you, and see you next year, Bologna.